Beneath the wavering curtains of a shallow reef, where sunbeams fracture through turquoise water into a dance of silver dust, a shape glides across the sand and vanishes. One moment it's a rippled shadow sliding above coral rubble. The next, it's gone, dissolved into the pattern of the seafloor. The sand doesn't move, yet something alive is there watching. The cuttlefish, master of illusion, has become the reef itself, a living, breathing deepfake, crafted by evolution's most ingenious artist. The cuttlefish's camouflage isn't a costume. It's an act of transformation so complete that it fools even the most advanced eyes in the ocean. While other animals rely on stillness or mimicry, the cuttlefish rewrites its entire surface in a heartbeat. Its skin is a screen of biological pixels, tiny sacs called chromatophores that expand and contract to reveal or conceal pigments of yellow, red, and brown. Deeper still lie iridophores and leucophores, specialized reflectors that scatter light and add the blues, silvers, and pearly whites that make its disguise shimmer like real coral, sand, or algae. Together they form an organic display system with resolution and response speed no human technology has yet matched. In less than 1 second, the cuttlefish can flip from shadow to blaze, from predator to rock, from invisible to luminous. When it moves over mottled coral, its skin flickers in precise coordination, blotches and stripes that map directly to the light patterns around it. If a passing cloud dulls the sun, its colors fade in tandem. The synchronization is so exact, it appears to predict rather than react, as though the cuttlefish sees the world not with eyes, but with skin. And in a way, it does. Its body is equipped with light-sensitive cells called opsins scattered across its skin, functioning as a secondary visual system. These cells detect changes in brightness and direction of light, giving the cuttlefish a primitive but invaluable global awareness of its surroundings. Combined with its extraordinary brain, proportionally larger than that of any other invertebrate, this sensory network allows the animal to process visual information and respond with perfect timing. A human artist might take hours to paint camouflage into a background. The cuttlefish achieves photorealistic concealment before a human heartbeat finishes. But its power extends beyond color. Texture is its second weapon. Beneath the skin, a lattice of muscular rings and papillae can raise or flatten the surface, changing the cuttlefish from glass smooth to coral rough in an instant. Sand grains, rubble, algae fronds, each can be imitated by adjusting skin texture. Watching this transformation is unsettling, like witnessing fabric reshape itself into stone. Even more remarkable, the cuttlefish often modifies both color and texture simultaneously, creating illusions of three-dimensionality so convincing that crabs and small fish swim directly into its reach. The cuttlefish's control over this complex system comes from a neural network that rivals vertebrate sophistication. Its brain sends electrical pulses that ripple through its body, generating dynamic waves of pattern, a biological light show. These waves aren't random. They can serve as communication, confusion, or intimidation. To hunt, the cuttlefish sometimes deploys a pulsing strobe pattern along its tentacles, a visual hypnosis that freezes prey in place. Small crustaceans caught in its gaze are mesmerized, their reflexes dulled just long enough for the cuttlefish's feeding tentacles to shoot forward and drag them into its beak. Every hunt is a performance, a blend of invisibility and sudden revelation. The cuttlefish doesn't chase, it deceives. It can pretend to be a patch of seaweed swaying harmlessly until a shrimp wanders close. Then, with a flash of contrasting stripes, a sudden act of unmasking, it lunges. The strike is surgical, powered by specialized tentacles that shoot out faster than a human blink. Once the prey is caught, a paralyzing saliva ends the struggle in seconds. What began as a show of disguise ends as a demonstration of precision engineering. For predators, however, the cuttlefish's illusions can mean the difference between life and death. Reef hunters like groupers, barracudas, and moray eels rely heavily on visual cues, yet many fail to recognize a cuttlefish until it's too late. Its camouflage isn't just static concealment, it's adaptive countershading, constantly updated by information from both eyes, which operate independently. Each eye can focus on a different object, giving it near 360-degree vision. And while humans are blind to polarization, the orientation of light waves, cuttlefish see it vividly. This hidden visual layer reveals contrasts invisible to most creatures, allowing them to spot camouflaged predators or other cuttlefish, even when color differences vanish. Polarization vision adds another layer to their secret world. When two cuttlefish meet, they can send polarized signals that appear invisible to other animals. To the untrained eye, their bodies might look plain, but through the polarization channel, their skin flashes coded information, a silent language encrypted in light. It's a biological encryption system, a secret ink that transmits identity, mood, and intent. Rival males may duel with polarized displays invisible to nearby predators, ensuring their combat doesn't attract unwanted attention. Yet the cuttlefish's most cunning deception is not in combat, but in love. During the breeding season, the seafloor becomes a theater of complex masquerades. Males display elaborate zebra-like patterns to assert dominance, their arms flaring and their skin flashing bold contrasts to impress females and intimidate rivals. But not all males are built to fight. Some, smaller and less dominant, use trickery instead. These sneaker males perform one of the ocean's most audacious acts of deception, the two-faced mating display. When a sneaker male approaches a female guarded by a larger competitor, he shifts his color and posture in halves. On one side, he shows the subdued, mottled tones of a female. On the other, he maintains the male pattern only visible to his target. To the guarding rival watching from the opposite side, the intruder appears harmless, just another female in the harem. But to the actual female, he's sending clear courtship signals. This split-screen disguise works because the cuttlefish can control each side of its body independently. Its brain halves coordinate different chromatophore patterns, a feat of neurological dexterity unseen in any vertebrate. As the dominant male relaxes, fooled by the apparent presence of two females, the sneaker slides in, mates covertly, and escapes before discovery. Studies in Australian waters have shown that such deceptive males can fertilize as many eggs as their larger, more aggressive counterparts. In the evolutionary playbook, brains and illusion can rival brawn. The complexity of these behaviors hints at an intelligence that defies the stereotype of invertebrates as simple automatons. In laboratory experiments, cuttlefish have demonstrated memory, problem-solving, and even self-control. They can learn through observation and remember specific past events, a form of episodic-like memory. When offered food immediately or after a delay, cuttlefish have been shown to wait for the higher quality reward, an ability once thought limited to vertebrates like crows and primates. It's as if the same brain that orchestrates instant camouflage also plans for the future, an odd pairing of impulse and foresight in a creature that lives barely 2 years. Their intelligence also guides their navigation through a world of constant danger. The reef is not static, it's a living maze that changes with tides, storms, and growth. Cuttlefish must constantly adapt, mapping their surroundings while managing threats from every direction. They rely on their jet propulsion to escape when illusion fails, a rapid expulsion of water through a siphon that rockets them backward, leaving behind a cloud of ink. But even that ink is more than a smokescreen. It's chemically complex, containing substances that dull a predator's sense of smell and taste. It's the oceanic equivalent of a flashbang, sensory overload in multiple dimensions. And then, as quickly as it fled, the cuttlefish can vanish again, settling into new terrain, rewriting itself to match it perfectly. Few animals embody adaptability so completely. In its short life, the cuttlefish becomes a hunter, an artist, a spy, and a magician, surviving through deception that goes far beyond hiding. Every skin flicker is a negotiation between visibility and secrecy, every texture shift a line between life and death. From an evolutionary standpoint, the cuttlefish's camouflage is not merely aesthetic, but functional on every level. It's a reflection of energy efficiency and neural control. Changing color and pattern takes little metabolic effort compared to the cost of fleeing or fighting. This efficiency has allowed cuttlefish to occupy ecological niches where visibility would otherwise mean vulnerability. Their soft, boneless bodies should make them easy prey, yet their adaptive genius has turned fragility into a survival advantage. Even their reproductive deception carries evolutionary weight. The diversity of mating strategies within a single species ensures genetic variation and flexibility in population dynamics. In ecosystems subject to rapid change, temperature shifts, reef bleaching, and pollution, such behavioral adaptability may spell survival. In this sense, the cuttlefish's illusions are not lies but adaptations, honest tools in a dishonest world. As the sun sets and the reef dims into twilight, the cuttlefish's colors shift again. The bright camouflage softens into ghostly translucence. A few bioluminescent plankton drift past, scattering faint green sparks, and the cuttlefish hovers motionless, its body faintly pulsing with hidden light. The sea around it is quiet, except for the faint hum of nocturnal life awakening. For now, its performance ends. Tomorrow it will become coral, rock, sand, predator, and lover again, whatever the moment demands. It lives not by force, but by illusion, rewriting its identity moment by moment. In the digital age, humans craft deepfakes to deceive each other. In the ocean, the cuttlefish has been doing it for millions of years, with no computer, no lens, no lies, only life itself reshaping to survive. The ocean floor is never truly still. Even when the tide slackens and the current slows to a whisper, small clouds of sand drift upward as something stirs below. A creature neither fully seen nor entirely hidden. Then, without warning, the seabed erupts in motion. A blur of arms and skin unfurls like a living parachute, and the world's most cunning escape artist steps into view. The octopus, soft-bodied, boneless, and armed with nothing but intelligence and instinct, is nature's ultimate illusionist. A creature that doesn't just adapt to its surroundings, but rewrites the rules of confinement, camouflage, and survival. Unlike most marine predators, the octopus carries no armor, no skeleton, no scales. Its defense lies in its flexibility, a body made entirely of muscle and mind. It can flatten itself to slide through openings no wider than an eye, compressing its entire bulk into crevices so narrow they seem physically impossible. To a predator, it can appear as solid as stone one moment and vanish into liquid shadow the next. Its soft anatomy, far from a weakness, has become the perfect blueprint for freedom. The absence of bones gives it access to spaces that no other large animal could occupy. This freedom of form is complemented by one of the most sophisticated nervous systems in the animal kingdom. 2/3 of its neurons lie not in its head, but in its arms. Each limb can act independently, tasting, touching, and thinking on its own, guided by an intelligence that operates in distributed fragments, a body that literally thinks for itself. The octopus's world is one of constant improvisation. Every day is an act of disguise, engineering, and escape. On the seafloor, it may wear shells, bottle caps, or halves of coconuts like armor, improvised gauntlets assembled from whatever the reef provides. These tools are not mere shelter, they are strategy. An octopus has been observed carrying 2 coconut halves across the sand, stacking them together like clamshell doors when danger approaches. Others gather piles of scallop shells, using them as shields or barricades, rearranging them with meticulous care. Scientists once dismissed such acts as random play, until it became clear that each piece was selected for function. The curvature of one, the thickness of another, revealing a level of planning once thought impossible in invertebrates. Its home, or den, is never just a hole in the rock. It's a stage set for both security and deception. Around the entrance, the octopus often piles the remains of past meals, crab claws, snail shells, fish bones, forming what divers call a bone midden. To a predator, these debris fields look like signs of death or scavengers, not a living occupant. But to the octopus, this litter is more than camouflage. It's a warning system. The crunch of a misplaced shell alerts it to approaching threats, while the scattered shapes break up its silhouette. Inside, the den is orderly and functional, with the octopus arranging objects and sediment to control its environment, a kind of architectural behavior almost unheard of in solitary marine animals. Yet the octopus's mastery extends far beyond the home it builds. When it ventures out to hunt, it becomes a shapeshifter of astonishing range. It can imitate rocks, algae, or even poisonous animals with uncanny accuracy. Some species flatten their bodies, changing color and texture to match the mottled sea floor, then walk on two arms, keeping the rest of their body still. A bizarre gait known as the decoy rock walk. To the casual observer, it looks like a piece of coral debris gently rolling in the current. This illusion is not just visual, but behavioral. The octopus matches its motion to the rhythm of the surrounding environment, timing its movements with passing waves to mask any sign of intent. The brilliance of this strategy lies in its layered deception. A predator that hunts by movement, say a moray eel, scans for motion against a static background. By mimicking the natural drift of inanimate objects, the octopus effectively vanishes from the eel's sensory map. It is not simply hiding, it is hacking the visual algorithm of its hunter. This is not instinct in the mechanical sense, it's learned behavior, refined through countless generations of trial and error. When attack becomes necessary, the octopus turns from illusion to ambush. In shallow reefs and sandy bays, the parachute pounce is one of its signature moves. Upon spotting prey, a crab, shrimp, or small fish, it silently extends its webbed arms outward in a wide arc, forming a living canopy. With a sudden contraction, it envelops its target, sealing every escape route in an elastic prison of skin and muscle. The prey doesn't even see it coming. The last thing it perceives is a descending shadow that was never there a moment ago. Then come the arms, working in eerie coordination, injecting venom through a sharp beak. In seconds, the scene is still again, and the octopus resumes its neutral tones, blending back into the landscape as if the strike never happened. Inside its body lies the machinery of a biochemical assassin. The octopus's saliva contains neurotoxins capable of paralyzing crustaceans instantly, along with enzymes that begin dissolving tissue before ingestion. This internal chemistry allows it to consume armored prey that other predators would ignore. Its beak, the only hard structure in its body, is razor-sharp and powerful enough to crack shells effortlessly. Some species, such as the blue-ringed octopus, take this arsenal further, producing tetradetoxin, one of the most potent natural poisons known. A dose small enough to fit on a pinhead can kill a human, though the octopus itself wields it only for hunting and defense. Yet the octopus's relationship with its environment is not defined by violence, but by ingenuity. Its intelligence manifests in ways that defy expectations. In laboratory settings, octopuses have unscrewed jar lids to access food inside, solved mazes, and even learned to recognize individual humans. Some have escaped from tanks, navigating drains and corridors to reach other enclosures, sometimes opening latches or valves along the way. One famous specimen, nicknamed Inky, escaped from a New Zealand aquarium through a gap no wider than a coin, crawling across the floor and sliding down a 50-meter drainpipe back to the sea. The story became legend, but for the octopus it was simply instinct, the perfect blend of curiosity and spatial awareness. What makes this possible is not just intelligence, but a kind of embodied cognition. Each arm functions as a semi-autonomous agent, equipped with its own mini-brain that can sense and manipulate without direct orders from the central nervous system. When an octopus explores, its arms probe with hundreds of suckers capable of detecting both texture and chemical composition. The world it perceives is not built from sight alone, but from touch and taste combined, a tactile, chemical landscape that humans can barely imagine. Through this sensory integration, the octopus constructs a detailed mental map of its surroundings, knowing not just where objects are, but what they are made of and how they behave in water flow. This sensory mastery extends to its camouflage as well. The octopus can change color through chromatophores, the same pigment sacs used by cuttlefish, but with even greater flexibility. Beneath these cells, reflective layers called iridophores scatter light in iridescent greens and blues, while deeper leucophores adjust to ambient brightness. The result is total control of light absorption and reflection, the ability to disappear in shadow or gleam under sunbeams. Even when resting, Micro-adjustments in its skin maintain perfect mimicry of the shifting environment. No predator can hold focus on it for long, but not all of its illusions are visual. The octopus is also a master of psychological misdirection. When threatened by a larger predator, it often releases a cloud of ink, a complex chemical mixture containing melanin, enzymes, and mucus. The dark plume creates a visual barrier, but it also carries substances that interfere with a predator's sense of smell and taste, disrupting its ability to track by scent. Sometimes the octopus molds the expelled ink into a cohesive blob that mimics its own shape, a ghostly pseudomorph. The predator attacks the decoy, while the real octopus jets away in another direction. In the language of warfare, this is counterintelligence, the use of deception to mislead pursuit. And when flight isn't an option, the octopus can simply vanish into structure, compressing its body into impossible crevices. No bones mean no fixed form. Once inside, it seals the entrance with shells or stones, sometimes rearranging them from the inside to create a barricade. Its suckers act like suction cups and hands combined, gripping surfaces with strength and finesse. Every motion is deliberate, calculated, the embodiment of silent defense. Perhaps the most extraordinary aspect of octopus life, however, is its balance between intelligence and impermanence. Despite its problem-solving skills and emotional complexity, an octopus lives barely 2 years, sometimes less. Its genius burns briefly and brightly. After mating, the female retreats to her den to guard her eggs, refusing food for months, fanning them with oxygen-rich water until they hatch. When they finally do, she dies, her final act one of sacrifice rather than escape. Her offspring drift into the plankton, miniature replicas of her, carrying the legacy of her intelligence into the currents. The paradox of the octopus is this: it is among the most intelligent of Earth's creatures, yet among the shortest lived. Every encounter, every tool, every deception must be learned anew by each generation. There is no cultural transmission, no parental teaching, only instinct layered over neural brilliance. This evolutionary path speaks to a truth deeper than any escape story, that intelligence itself can emerge wherever the environment rewards adaptability, even if it burns out quickly. The octopus's mind evolved not for longevity, but for survival in an unpredictable three-dimensional labyrinth. When the current sweeps across the reef at dusk, the octopus emerges once more, arms drifting like banners. Its skin flickers between coral red and sand beige, scanning for opportunity. It glides toward a cluster of shells, rearranges them slightly, and pauses. To the casual eye, it's just another patch of seafloor. But beneath that stillness lies the ocean's most sophisticated con artist, a creature that turns vulnerability into weaponry, chaos into strategy, and confinement into illusion. Tomorrow, perhaps, it will escape again. Not from an aquarium, but from a predator's jaws, a collapsing cave, or the expectation that such brilliance should belong only to vertebrates. In the end, the octopus's greatest illusion is not its color or its camouflage, but its defiance of limits. In a world built of barriers, bone, shell, structure, it remains pure possibility, a shape without boundary, a mind without walls. Beneath the muted shimmer of a tropical lagoon, where the water runs shallow and the sun filters through in fractured beams, lies something that looks entirely lifeless. It's a lump of coral rock, half buried in silt, a shape so dull and unremarkable that even the crabs ignore it. The current slides over it without resistance, dusting its outline with fine grains of sand. Yet under that motionless crust is one of the most efficient killing machines on Earth, a fish so well disguised that death itself would have trouble telling the difference. The stonefish does not hunt with speed or stealth in the traditional sense. It simply waits, a corpse with a pulse, biding time until something makes the mistake of thinking it's safe. Its camouflage is absolute. The skin is a map of deception, warty, encrusted and mottled with shades of grey, brown and ochre that perfectly match the rubble and algae of the seafloor. Even under close inspection, it's nearly impossible to distinguish from a dead coral fragment or a discarded shell. Over time, living algae and small invertebrates even grow on its surface, enhancing the disguise with natural texture. This isn't passive evolution, it's the product of selective perfection, where only those who could hide well enough to outlast both prey and predators survived. The result is an organism that doesn't just resemble the seafloor, it is the seafloor until the moment it decides not to be. The stonefish's greatest weapon is patience. Unlike predators that roam or stalk, it lives its life anchored to stillness. Motion gives away intent, and intent in the reef is death. So it rests, barely breathing, its gill flaps pulsing once every few seconds. The entire body is a coiled trap, a system of muscular tension waiting to be released. Then, in a movement so fast the human eye can barely register it, the stonefish explodes into life. A flash of suction, a blur of jaws, and the victim, often a small fish or shrimp, is gone. The attack takes less than a millisecond. Not even the prey's nervous system reacts before it vanishes down the predator's throat. This speed is no accident. The stonefish's jaw mechanism works on a hydraulic principle. The mouth cavity rapidly expands, creating a sudden vacuum that pulls water and prey inward faster than the prey can flee. It doesn't bite or chew, it simply opens and consumes. Inside, specialized gill arches and pharyngeal muscles compact the captured water, forcing it out and leaving the meal behind. The entire event is over before the surrounding sand has time to settle. It is ambush predation distilled to its purest, most efficient form: strike, swallow, reset. Resetting is part of the act. After every kill, the sand and silt around the stonefish are disturbed, a trace that could betray its presence. To erase this evidence, it performs what scientists call the sand jet reset. By rapidly expelling jets of water from its gills, the stonefish clears and rearranges the sediment, blending itself once more into its surroundings. The precision of this behavior is astonishing. The fish doesn't just hide under sand, it sculpts its camouflage, positioning grains and debris to perfectly match the neighboring textures. It's an artist of invisibility, refining the illusion after every performance. The ecosystem it inhabits, shallow tropical reefs and estuaries, demands such perfection. These zones are crowded, chaotic, and noisy with life. Every organism here is both hunter and hunted, and visibility often means vulnerability. Many predators, from herons to rays, rely on movement or contrast to detect prey. The stonefish, immobile and color-matched, falls beneath that perceptual threshold. Its stillness isn't laziness, it's a physiological adaptation. Its slow metabolism allows it to remain motionless for days, even weeks between meals, conserving energy in the way only an animal built for ambush can. But this stillness carries risk. For an animal that looks exactly like a rock, there's the constant danger of being mistaken for one, particularly by creatures much larger than itself. Divers and fishermen throughout the Indo-Pacific have learned this the hard way. Stepping on a stonefish is one of the most painful accidents in the marine world. The reason lies in its final, sinister line of defense, a row of venomous spines along its dorsal fin. Each spine is connected to a pair of venom glands embedded deep within the tissue. When pressure is applied, for example by an unwary foot, the spine punctures skin and muscle, injecting a dose of potent neurotoxin. The venom, composed of proteins such as stonefish and barracuda, triggers massive pain, swelling, and in severe cases, paralysis or cardiac failure. Unlike many defensive toxins that simply deter, stonefish venom actively disrupts physiological function, interfering with nerve signaling and blood flow. To a small predator, this means instant death. To a human, hours of excruciating agony. What's particularly cruel is that the fish's passive appearance often encourages the accident. Unlike brightly colored warning species, the stonefish gives no visual signal of danger. Its defense is not deterrence but vengeance, a booby trap set for the careless. The venom isn't always fatal to humans, but it has earned the animal a grim reputation as the most venomous fish on the planet. The irony is that it rarely uses this weapon offensively. The spines are defensive only, reserved for those who attack or step too close. To hunt, the stonefish relies not on poison, but on physics, the near-perfect control of water pressure and speed. In the context of reef ecology, the stonefish plays a crucial yet underappreciated role. Its ambush predation helps regulate populations of smaller reef fish and crustaceans, maintaining the delicate balance of the ecosystem. By targeting weak or unwary individuals, it indirectly strengthens the genetic resilience of prey populations. The same evolutionary filtering that apex predators perform in larger systems. Even its venom contributes to ecological balance. Scavengers that feed on its carcass after death must do so carefully, ensuring that only those adapted to handle its toxins survive. Surprisingly, despite its lethality, the stonefish itself faces predators. Sea snakes, particularly species like the olive sea snake, are known to prey upon it, seemingly immune to its venom. Their immunity likely evolved from a biochemical arms race, predators adapting to toxins over generations. Sharks, too, occasionally consume stonefish whole, their thick skin and digestive enzymes neutralizing the venom before it can take effect. This dynamic exemplifies a broader evolutionary truth: no defense is perfect forever. Even the most dangerous creature is simply another link in nature's endless loop of adaptation. The stonefish's camouflage, though extraordinary, is not static. Individuals can subtly adjust coloration over days to better match new environments. Specialized pigment cells, or chromatophores, expand or contract to modify hue and brightness. This is not the dynamic color flashing of cuttlefish or octopus, but a slow, deliberate recalibration, long-term camouflage maintenance rather than moment-to-moment disguise. Combined with dermal spinules and fleshy outgrowths that mimic coral polyps or algae tufts, it creates a living sculpture of decay that renews itself continually. Its hunting strategy is equally nuanced. Studies using high-speed cameras have revealed that stonefish can modulate their strike speed depending on prey behavior. Against slower targets, they conserve energy with controlled suction. Against fast-swimming fish, they unleash maximum velocity, creating a stronger vacuum pulse. The neural circuits controlling this strike are astonishingly precise. A microsecond-timed coordination of cranial muscles, jaw hinge expansion, and buccal cavity dilation. It's one of the fastest feeding reflexes in the vertebrate world, rivaled only by the snapping jaws of seahorses and frogfish. Perhaps the most fascinating aspect of the stonefish is how its evolutionary path embodies paradox. Everything about its biology seems designed for stillness, yet its strike is defined by explosive power. It's a predator that has perfected death's disguise, yet it must remain alive, alert and reactive beneath that mask for days on end. Its venom is among nature's most painful, yet it's used rarely and reluctantly. Evolution has not built the stonefish for aggression or dominance. It has built it for inevitability. It doesn't chase prey. It lets the world come to it, and the world always does. From an ecological perspective, this lethargic ambusher represents a different model of success. Not one driven by mobility or social complexity, but by the mastery of patience and precision. In coral ecosystems increasingly stressed by warming seas, the stonefish may even gain advantage. As bleaching events strip reefs of color and complexity, more rubble and dead coral accumulate, exactly the kind of environment it thrives in. The death of the reef becomes the canvas of its camouflage. Nature's cruel symmetry continues. One species' collapse becomes another's opportunity. As dusk falls over the lagoon, the light fades to amber and then to gray. Schools of juvenile fish drift above, their scales catching the last glints of sun. Among them lies the same motionless shape unmoved by time. A damselfish wanders too close, pecking at the sand, unaware that the rock beneath it breathes. The stonefish stirs. A puff of sediment rises, then silence. When the cloud clears, the damselfish is gone, and the stone returns to stillness. In the theatre of the reef, where color and motion define life, the stonefish is the quiet contradiction. It is ugliness perfected into efficiency, lethality disguised as decay. Its genius lies not in what it does, but in what it doesn't, the art of waiting, the science of remaining unseen. To witness it up close is to confront one of evolution's darkest jokes, that sometimes the most lifeless-looking thing on the ocean floor is the one most capable of killing you. In the cold grey shallows of the North Atlantic, where sunlight struggles to pierce the churning water and the seafloor looks more like a graveyard than a home, a shadow waits. It is not the sleek silhouette of a hunter in motion, but something flattened, distorted, and wrong, a creature designed not to chase, but to deceive. The monkfish lies pressed against the mud, fins spread wide like wings of flesh, eyes set high on its broad head. To the untrained gaze, it is simply another patch of sand, perhaps a scrap of discarded kelp. But beneath that disguise is a living paradox, a predator that lures the curious by pretending to be harmless. It is the ocean's consummate con artist, and its trick is as elegant as it is lethal. The monkfish, also known as the goosefish or angler of the continental shelf, belongs to the family Lophiidae, a group of deep-bodied ambush predators that have traded grace for guile. Its anatomy is a map of adaptations built for one purpose: to lure and consume. Its enormous, flattened head accounts for nearly half its body length, ending in a mouth that seems less an organ and more a doorway, a gaping, expandable cavity lined with backward curved teeth. This is not a mouth that bites, it engulfs. When fully opened, the gape is so wide that fish nearly as large as the monkfish itself can vanish inside. Yet even this monstrous maw would be useless without the weapon that gives the species its identity: the elysium, a flexible, rod-like extension of its dorsal spine tipped with a fleshy lure called the esker. This lure is the key to the monkfish's deception. Perched on the crown of its head, it twitches, coils and wriggles like a living worm, an irresistible signal to any small creature searching for an easy meal. The motion is powered by fine muscle control, subtle enough to mimic the spasms of injured prey. To a passing codling or haddock, it is the promise of food. To the monkfish, it is a fuse waiting to be lit. As the victim drifts closer, the predator remains utterly still. Every fin edge is pressed into the substrate, every breath slowed to invisibility. Only the lure moves, a flicker of life against a background of death. Then, in an instant shorter than a heartbeat, the stillness erupts. The monkfish's jaws swing upward like trapdoors, and the vacuum they create sucks in a torrent of water, prey and all. The entire strike takes less than 1/6 of a second. No chase, no pursuit, only an explosion of negative pressure and perfect timing. The teeth ensure that nothing escapes. Their inward curve traps anything unfortunate enough to cross the threshold. For the victim, the world simply folds inward and light vanishes behind the curtain of flesh. The precision of this mechanism reflects an evolutionary arms race honed over millions of years. In most fish, the jaw muscles operate primarily in tension, pulling the mouth closed. In the monkfish, the entire cranial architecture is modified to amplify suction. When the upper jaw lifts, the buccal cavity below expands like a bellows, creating a sudden drop in internal pressure. Water, and whatever floats within it, rushes in to equalize the difference. It is a weapon of physics as much as biology, one that transforms the entire head into a living vacuum pump. Once inside, the prey meets a second trap. The monkfish's stomach can stretch to accommodate enormous volumes, allowing it to swallow meals nearly half its own mass. But what makes the monkfish even deadlier is where it lives. Unlike its deep-sea relatives, which hunt in perpetual darkness, this species thrives on daylight shelves, the sloping regions of ocean floor where light still penetrates and productivity blooms. Here, the seafloor teems with life, shoals of sand eels, benthic crustaceans, flounder, and juvenile fish drawn by the rich upwelling of nutrients. The monkfish sits at the junction of two worlds, illuminated enough for prey to see its lure, but dim enough for its camouflage to work flawlessly. Evolution has optimized it for this twilight balance. Its coloration mirrors the sediment beneath, mottled browns, greys, and creams arranged in broken patterns that mimic ripple marks left by the tide. The skin itself is covered with a thin layer of mucus and fine dermal filaments that trap particles of silt, blending the fish into the substrate so completely that only its eyes, two small orbs perched like periscopes, betray its presence. Those eyes can move independently, scanning the water above while the rest of the body remains inert. Unlike many ambush predators that rely solely on motion detection, The monkfish processes both visual and hydrodynamic cues. Tiny pressure sensors embedded along its lateral line detect the faint disturbances caused by nearby swimming, a living sonar that maps the water column in invisible ripples. The combination of senses allows it to judge not only distance but also trajectory, enabling precision strikes even in murky conditions. When the moment arrives, the attack is coordinated through a lightning-fast neural circuit connecting the eyes, lateral line, and jaw muscles, a reflex system so finely tuned that no conscious decision is required. This is instinct elevated to mechanical perfection. Yet there is more to the monkfish's lifestyle than pure ambush. Its ecological role on the continental shelf is one of quiet regulation. By preying on smaller demersal species, it prevents overpopulation and maintains balance in communities that would otherwise collapse under competition. It is, paradoxically, both a destroyer and a stabilizer, a keystone predator whose presence ensures that the web of life on the seafloor remains intact. Its hunting method, though brutal, is also remarkably efficient. Unlike active hunters that expend energy in pursuit, the monkfish burns almost none. It can go days without feeding, relying on a slow metabolism and the occasional windfall of large prey. In an environment where food supply fluctuates with the seasons, this energy thriftiness is an evolutionary triumph. The bait-and-switch strategy also has an eerie beauty when seen from an evolutionary perspective. It represents one of nature's rare cases of aggressive mimicry, where a predator uses imitation to deceive rather than to hide. Other examples, such as the anglerfish of the abyss or the mantis shrimp's feigned passivity, pale in comparison to the monkfish's sophistication. The Elysium is not a passive ornament, it's a finely tuned sensory extension. Inside it run tiny nerves that help the fish gauge the tension and current flow around the lure. It can tell when something brushes the tip, when a potential prey hovers near, and when to strike. It's a form of tactile premonition. The predator can feel curiosity before it becomes contact. This deceptive elegance is amplified by the monkfish's remarkable adaptability. When storms churn the seabed or currents shift sediment patterns, it relocates using slow, deliberate fin crawls, an undulating walk rather than a swim. The pectoral fins, thick and limb-like, function almost as arms, pushing and anchoring the body forward. Each movement raises a brief puff of mud, which quickly settles, restoring invisibility. It's a primitive but efficient method of locomotion that keeps the fish close to the bottom where its disguise remains effective. Its reproductive strategy mirrors this strange duality between patience and abundance. During spring, females release long ribbons of gelatinous egg masses, sometimes stretching several meters, that drift near the surface like translucent veils. Each ribbon contains hundreds of thousands of eggs suspended in neat hexagonal chambers. When the larvae hatch, they are pelagic, living among plankton far above the realm of their parents. Only after weeks of drifting do they sink to the seafloor and transform into miniature versions of the adult, a shift from openness to concealment, from sunlight to shadow. Evolution has given the species two worlds to master: the free-floating chaos of the planktonic stage and the absolute stillness of the adult. What makes the monkfish's story compelling is that it thrives in an environment defined by paradoxes. The continental shelf is both fertile and deadly, offering food in abundance but also exposure to predators. To survive here, most fish evolve speed, schooling behavior, or cryptic flight responses. The monkfish chose the opposite route. It abandoned movement, embraced ugliness, and turned deception into art. Its grotesque face, with teeth protruding like shattered glass, is not a flaw but a tool. Every curve of that mouth, every rough patch of skin, contributes to a single purpose: to convince others that it is harmless until the final instant. Even the physics of its habitat favors its strategy. Daylight shelves create a complex mosaic of light and shadow, with waves refracting sunlight into shifting patterns. This constant movement of brightness across the seabed makes it nearly impossible for other creatures to discern shape by outline alone. The monkfish's irregular profile, combined with its motionless posture, allows it to vanish into these optical distortions. The environment itself becomes part of its disguise, a dynamic camouflage maintained not by the fish, but by the sea. And yet, for all its cunning, the monkfish's own predators see through the illusion. Large sharks and seals occasionally capture them, guided by electroreceptive senses that detect the faint bioelectric fields generated by living tissue. No disguise can hide life's current forever. Still, such encounters are rare. Most threats to the monkfish now come from above, not from other animals but from humans. Its firm white flesh, once dismissed as unmarketable, has become a delicacy known as poor man's lobster. In some fisheries, overharvesting has pushed populations to the brink, turning this ancient ambusher into prey for the most efficient hunter of all. Yet even in decline, the monkfish endures as an emblem of evolutionary cunning, proof that survival in the ocean isn't about strength or beauty, but about understanding how to manipulate perception itself. Beneath the waves, deception can be more powerful than speed, patience more deadly than aggression. As the camera drifts over a silted plain, a wriggling thread appears among the pebbles. Just a harmless worm, it seems, dancing in the current. A small fish glides closer, lured by hunger and the illusion of opportunity. Then the sand erupts. A mouth opens where no mouth should be, and the ocean swallows its lesson whole. Dusk settles over the coral reef like a soft exhale. The chaos of daytime feeding fades, and the riot of colors dulls under the descending blue. Tiny fish retreat to crevices, crabs seal themselves into coral pockets, and the reef's daytime giants drift into deeper water. For a moment, peace seems to settle, a deceptive calm broken only by the hum of nocturnal life beginning to stir. Then, gliding through the dim lattice of coral spines, something moves with a rhythm too smooth, too deliberate to belong to the drifting current. The lionfish has arrived, and with it comes one of nature's most mesmerizing forms of predation, a ballet of beauty and hypnosis, of motion so slow it becomes irresistible. The lionfish is an ambush predator that has evolved patience into an art form. Unlike the quick striking hunters of the open sea, its weapon is not speed but illusion. Its entire anatomy is a study in contradiction, a fusion of flamboyance and lethality. Long, feathery fins trail from its body in radiant fans of red, white, and black, fluttering like silk veils in the current. To the uninitiated, it looks more ornamental than dangerous, a creature designed for display, not attack. But this velvet beauty conceals an intricate system of deception, control, and precision that makes it one of the most efficient ambushers in the marine world. The strategy begins with posture. The lionfish spreads its pectoral fins wide, forming an elegant semicircle around its body. These fins, each supported by flexible rays, can span nearly twice the width of the fish itself, creating what appears to be a delicate, translucent net. But this display has purpose. The extended fins manipulate both light and movement in the surrounding water, herding small prey like damselfish and cardinalfish into confined space. The fins create barriers that the prey misinterpret as impassable, visual walls in an environment where sight governs escape. The illusion works because reef fish rely heavily on peripheral visual cues to gauge threat distance. The lionfish, by exaggerating its size with its fan-like extensions, silently rewrites those cues. Unlike most predators that trigger flight responses through abrupt motion, the lionfish advances with agonizing slowness. Its approach is so controlled that its movement blends seamlessly with the rhythm of the current. Each fin beat is a calculated whisper, propelling it forward millimeter by millimeter. This slow-motion stalking lowers the prey's perception of danger. Many reef fish interpret only rapid acceleration as threat. The lionfish's steady glide falls beneath that sensory threshold. By the time the prey realizes something is wrong, the predator is already within striking distance, close enough that even the slightest twitch would seal their fate. As it advances, the lionfish's striped pattern plays its second trick. The alternating bands of light and dark distort its outline, breaking up the perception of shape and motion. This phenomenon, known as motion dazzle, confuses visual processing in other fish, making it difficult to track the lionfish's trajectory. In low light, this effect is amplified by the soft shadows of coral and rubble, creating an optical field in which the predator seems to flicker between presence and absence. To the prey, it's as though the lionfish is simultaneously moving and still, a contradiction their instincts can't compute. Then comes the final act, the freeze. Within a meter of the target, the prey stops moving entirely, as if paralyzed by indecision. The cause of this behavior has puzzled scientists for years. Some suggest it's a neurological overload, the prey's sensory systems locked by conflicting signals from the lionfish's expanding fins and undulating stripes. Others believe it's the product of subtle hydrodynamic manipulation. The slow sweep of the lionfish's fins generates microcurrents that disturb the lateral line sensors along the prey's body, the organs that detect movement and vibration in water. When these signals become too chaotic to interpret, the prey's response system fails, freezing it in place. Whether psychological or mechanical, the result is the same. The victim becomes still, suspended in fatal calm. The strike itself is almost anticlimactic. A single inhalation, a sudden flare of gill covers, and the lionfish's mouth expands into a vacuum that engulfs its target. The entire event lasts less than 1/10 of a second. No chase, no struggle, only a flicker of fins, and the reef returns to silence. Unlike other predators that rely on brute force or venom to subdue prey, the lionfish's success lies in its ability to neutralize panic before the attack even begins. The prey doesn't flee, it surrenders. By night, this theater of hypnosis reaches its peak. The lionfish becomes a moving shadow among shadows, gliding through coral branches and rubble fields with ghost-like ease. Its eyes, highly adapted to low light, amplify even the faintest bioluminescence. Specialized rods in its retina allow it to perceive motion in near darkness, granting it the precision of a spotlight in the dim glow of the reef. Unlike diurnal hunters that depend on color contrast, the lionfish's vision is tuned to brightness gradients and polarization, the subtle angles of light reflected off scales and shells. This gives it an edge over nearly all nocturnal prey, whose camouflage fades once the sun disappears. The night hunt also exposes another layer of its strategy, cooperation. Though solitary by day, lionfish sometimes form small hunting groups after sunset. They coordinate loosely, spacing themselves a few meters apart, driving prey out of hiding with synchronized fin sweeps. When cornered, one lionfish blocks escape while another strikes. It's not communication in the human sense, but a mutual understanding, a convergence of opportunity. Such temporary alliances highlight an overlooked aspect of their intelligence, the ability to recognize efficiency beyond individuality. In this silent choreography, they become living nets that tighten from all sides until the reef's smaller residents vanish into their collective mouths. Beyond the immediate spectacle of the hunt lies a deeper ecological truth. The lionfish is a master of exploitation. Its strategies evolved for the complex, species-rich reefs of the Indo-Pacific, where stealth and precision were essential to survival. Yet these same traits have made it catastrophically successful in regions far from home. In the Western Atlantic and Caribbean, where it has become an invasive species, the local fish have no evolutionary experience with its tactics. They do not recognize the fin-fan display as a threat, nor the slow approach as a signal of predation. As a result, entire reef systems have been reshaped by its proliferation. Juvenile fish populations decline, herbivorous species vanish, and algae begins to overgrow the coral, altering the entire ecosystem. The lionfish, with its velvet movements and hypnotic grace, becomes not just a predator, but an ecological invader, a case study in how beauty can mask catastrophe. Its venomous spines add a final dimension to this story. Along its dorsal, pelvic, and anal fins, hollow spines connect to venom glands that secrete a potent neurotoxin. For predators that might mistake its slow movement for weakness, these spines deliver immediate correction. When threatened, the lionfish flares its fins outward, transforming its body into a spiked fortress. Few attackers dare to test the warning. Even sharks, which typically ignore the threats of smaller fish, have learned caution around these floating mines. For the lionfish, the venom is not an offensive tool, but a guarantee of freedom, the confidence to move unhurried through dangerous territory. and that unhurried rhythm defines everything about its existence. The lionfish's entire life is paced to the slow pulse of coral currents, its energy economy finely tuned to efficiency. It can go days without feeding, conserving metabolic resources through reduced muscle activity and selective motion. Its fins are not built for speed, but for control, broad feathered planes that allow it to hover with surgical precision. Even respiration is calculated. By pulsing water gently over its gills instead of swimming constantly, it minimizes both energy expenditure and acoustic signature. In a world where motion often means survival, the lionfish thrives by defying urgency. Yet perhaps the most remarkable part of its hunting success is psychological. The lionfish weaponizes perception itself. Its fins are too large, its movement too delicate, its posture too theatrical for most reef species to categorize. Prey that have evolved to recognize silhouettes of typical predators, streamlined, darting, aggressive, simply do not interpret this shape as dangerous. The lionfish slips through their cognitive blind spots, a predator hidden not by invisibility, but by disbelief. Evolution teaches animals to fear what they've seen before. The lionfish survives by looking like something they've never seen at all. As night deepens and the current picks up, the lionfish drifts back toward the reef ledge, settling near a patch of soft coral. The fins fold partially inward, the stripes merge with the dim ripples of moonlight, and the body becomes motionless once more. Tiny shrimps scuttle past its face, unaware of how narrowly they escape. The ocean around it is alive with the quiet hum of nocturnal activity, the soft rasp of parrotfish scraping coral, the clicking of distant crabs, the faint echo of dolphins calling in the distance. But in this corner of the reef, all sound feels dampened, as if the water itself holds its breath. Then, somewhere in the darkness, another flicker of fins opens like a blooming flower. A second lionfish moves into view, both predator and performer, ready to weave another act in this velvet theater of death. The hypnotist of the reef has no need for speed or brute strength. It conquers through calmness, through beauty, through the mastery of illusion. In the end, its deadliest weapon is not its venom or its teeth, but its ability to make the living forget that death is near. In the calm shallows of a tropical bay, sunlight refracts through rippling water, painting the sand below with a shifting mosaic of light. Small schools of fish flit between coral heads, grazing on plankton and algae, while sea cucumbers inch lazily across the bottom. Among this ordinary tranquility drifts a creature that seems harmless, almost clumsy. A round-bodied fish with an uncertain wobble to its swimming, propelled not by the confident beats of a tail fin, but by tiny flutters of its pectoral fins. It is the pufferfish, the unassuming jester of the reef. Yet beneath that almost comedic appearance lies one of evolution's most sophisticated defense systems, a two-tiered strategy that combines theatrical deception with biochemical warfare. At first glance, the pufferfish's very body shape defies logic. It is not built for speed or agility. Its fins are small, its tail weak, and its movements inefficient in open water. In a realm where survival often favors sleek, fast bodies, the puffer seems an evolutionary misstep, a fish that should have been eliminated long ago by the relentless filter of predation. But the puffer's survival does not depend on escape. Its genius lies in deterrence, a strategy built on making itself an unworthy or impossible meal. The first stage of this defense is pure theater. When threatened, the puffer performs one of nature's most extraordinary transformations. It inflates. Specialized elastic stomach tissue allows the fish to gulp water, or air if caught above the surface, expanding its volume several-fold in a matter of seconds. Muscles at the base of the esophagus seal tightly, trapping the intake within, while connective fibers in the skin stretch to near translucent limits. The sudden metamorphosis turns the puffer from a palm-sized morsel into a spiked balloon, nearly impossible for a predator to swallow. This is the inflation theater, an act of pure intimidation, meant to shock and confuse attackers before the real danger even begins. The physics of this transformation are remarkable. In some species, the expansion increases body diameter by more than 200%, changing not just size, but density and maneuverability. As the body inflates, the center of gravity shifts, causing the fish to rotate slightly upward, fins trembling as it hovers like a drifting buoy. For predators used to pursuing streamlined targets, the sudden appearance of this awkward, inflated orb disrupts their attack pattern entirely. Many stop in confusion, circling and inspecting what now seems less like prey and more like an alien object. For reef hunters like groupers or moray eels, whose jaws are designed for suction feeding, an overinflated puffer can actually be deadly to swallow. The fish may lodge inside the predator's throat, blocking respiration and killing both hunter and hunted. Some species enhance the illusion further with spines. Normally flattened against the body, these sharp dermal structures pop outward when the fish inflates, creating a hedgehog-like armor. In the porcupine fish, a close relative of true puffers, the spines are so pronounced that they form a nearly impenetrable barrier once extended. Underwater, this display looks almost mechanical, a rapid unfolding of defensive architecture powered entirely by internal pressure. It's evolution's version of a medieval mace emerging from a child's toy. But the puffer's real weapon lies not in its skin or size, but in its chemistry. Hidden within its tissues is tetradetoxin, one of the most potent neurotoxins known to nature. Produced not by the fish itself, but by symbiotic bacteria that inhabit its organs and skin, the toxin serves as a molecular shield. Tetradetoxin blocks sodium channels in nerve cells, halting electrical transmission. In practical terms, it shuts down the nervous system with surgical precision. For predators that bite into a puffer, even a trace amount can cause paralysis within minutes. The heart continues to beat, but the muscles no longer obey the brain's commands. There is no antidote, no recovery, only stillness. What makes tetradetoxin particularly insidious is its invisibility. It has no smell, no taste, no visual cue. Many predators encounter it only once. The lesson it teaches, through death or near death, is enough to establish the puffer's reputation across ecosystems. Young predators that survive their first taste test learn quickly, associating the puffer's distinctive shape and color with nausea, paralysis, or worse. This learned avoidance creates an evolutionary ripple effect. Entire species develop instinctive recognition of puffers as dangerous, reinforcing the fish's survival strategy without it ever needing to use its toxin. Yet the puffer's defense system is not always absolute. In areas where puffers share space with specialized predators, such as tiger sharks or sea snakes, immunity evolves. Some snakes can ingest puffers without harm, having developed resistance to tetradetoxin through genetic mutations that alter their sodium channels. This evolutionary arms race exemplifies nature's constant balance of power. Every weapon invites a countermeasure, every adaptation a response. Still, for the majority of the reef, the puffer's dual defense remains untouchable, a bluff that kills even when it is only half believed. For the puffer itself, these defenses enable a lifestyle few fish can afford. Lacking speed, it drifts among corals and seagrass beds with deliberate calm, feeding on crustaceans, mollusks, and algae. Its beak-like jaws, formed by the fusion of 4 teeth, crush through shells and coral fragments with astonishing force. Inside the mouth, secondary grinding plates pulverize food into digestible particles. This dentition, continually growing throughout its life, allows the puffer to exploit hard-shelled prey others cannot access, reducing competition for food. Every crunch of crab shell or clam casing echoes the evolutionary advantage of a fish built not for flight, but for endurance. Among the 400 known species of pufferfish, one stands apart for behavior that transcends defense or feeding, the circle nest artist of the Japanese Pacific. In the shallows off southern Japan, a male white-spotted puffer becomes an engineer of the seabed. Over the course of a week, he uses his fins to sculpt a geometric nest nearly 2 meters wide, an intricate circular pattern of ridges and valleys etched into the sand. Each ridge is carefully fanned into symmetry, forming a starburst design that captures drifting shells and coral fragments, which the male arranges as decorative accents along the outer ring. The nest's purpose is purely reproductive, yet the process demands constant labor. Currents threaten to erase the pattern, forcing the artist to work tirelessly, maintaining precision against the tide. When a female approaches, she inspects the structure, assessing its symmetry and stability. If it meets her standards, she deposits her eggs at its center, where the male fertilizes and guards them until they hatch. When the larvae finally drift away, the nest is abandoned, soon erased by the shifting sand. Art created for a single moment of approval, then lost forever. This behavior highlights an unexpected dimension of puffer intelligence. Despite their comical appearance, puffers exhibit problem-solving skills and spatial awareness rarely seen in fish. In captivity, they recognize individual humans, learn feeding schedules, and can manipulate objects with remarkable dexterity. Their eyes, capable of independent movement, grant them near panoramic vision, a critical adaptation for a species that must detect threats from every angle. They also possess a unique vestibular system that stabilizes their gaze even while rotating, giving them exceptional control during their inflation maneuvers. It is an evolutionary irony. A creature that looks perpetually startled is, in truth, astonishingly composed. The relationship between bluff and bioweapon in the puffer's life is more than redundancy. It is layered defense psychology. The inflation display deters impulsive attackers, those motivated by movement and size. The chemical toxin targets those who persist despite the warning. Together, they form a sequence of escalating consequences, a biological security system that filters threats by commitment. Even the puffer's bright patterns, from spotted skins to swirling stripes, function as aposematic signals, warning potential predators of toxicity. In the clear shallows where visual communication reigns, these colors are not decoration, but proclamation. I am not worth your risk. And yet the puffer's greatest threat comes not from the reef, but from humanity. In Japan, the fish is both revered and feared as fugu, a culinary delicacy prepared only by licensed chefs who train for years to remove the toxic organs without contaminating the flesh. Even a tiny mistake can prove fatal. Ironically, it is this peril that elevates the dish's status, danger transformed into luxury. In consuming the puffer, humans mirror the same fatal curiosity shown by its natural predators, the compulsion to test the boundary between caution and temptation. Back in the wild, the puffer drifts once more among the corals. A shadow passes, a barracuda, fast and sleek, eyes glinting with predatory intent. The puffer does not flee. Instead, it swells with water, spines erect, body ballooning into a sphere. The barracuda lunges, then halts abruptly, jaw half open, recognition dawning too late. It veers off, confused, unwilling to gamble. The puffer slowly exhales, shrinking back to normal size, fins trembling lightly in the aftermath. Around it, the reef resumes its motion, unbothered, unafraid, unaware that beneath that gentle smile lies one of the most refined defense systems evolution ever devised. It floats onward, the perfect contradiction, fragile yet deadly, naive in appearance but armed with biochemical precision. In a world built on speed and strength, the puffer survives through artifice, the bluff that saves its life, and the poison that ensures no one forgets why. At first glance, the reef looks tranquil, a cathedral of light and color where coral pillars sway and fish flicker like confetti in the water's glow. But within this serene chaos, buried among burrows and rubble, lives one of the most extraordinary predators on the planet. A creature that sees a world invisible to almost every other eye, speaks in light no other animal can read, and kills with the speed of a bullet. The mantis shrimp is not large, scarcely the length of a human hand, yet in the microcosm of the coral reef, it is a force of almost mythic precision. Its claws can strike with the acceleration of a gunshot, its vision spans wavelengths from ultraviolet to polarized light, and its behavior is a study in both restraint and violence. Evolution has sculpted this animal into a paradox, the perfect warrior who prefers not to fight. The world of the mantis shrimp begins in its eyes, twin orbs that bulge from its head on independent stalks, scanning the environment in a way no human brain can fully comprehend. Each eye is a self-contained computer, divided into 3 parts that see color, polarization, and depth simultaneously. Where humans rely on 3 color receptors, mantis shrimp have up to 16, including one sensitive to ultraviolet and circularly polarized light. This means they perceive not just hue, but the direction and rotation of light waves, a hidden language of the ocean that most creatures never glimpse. To the mantis shrimp, the reef is alive with coded messages, reflections, flashes, and iridescent whispers of communication among species that cannot understand one another. Among their own kind, these shrimp use polarization patterns on their bodies like invisible warning flags. The exoskeleton, coated in specialized microstructures, reflects polarized light in complex patterns that can only be detected by other mantis shrimp. It is a private signaling system, evolution's encryption. Two rivals can exchange visual threats or display territorial boundaries without alerting nearby predators or prey. To a passing fish, the mantis shrimp looks ordinary, perhaps even dull. But to another of its species, it glows with unmistakable color, signatures of dominance, readiness, or aggression. This communication method drastically reduces conflict in a world where violence could be fatal, even for the victor. Because when mantis shrimp fight, the consequences are catastrophic. Their weapons, raptorial appendages folded beneath the head, are biological hammers or spears depending on the species. In the smasher types, the clubs strike with a velocity that breaks the sound barrier underwater, generating not only physical impact, but shockwaves strong enough to crack aquarium glass. In the spearer types, the claws are barbed lances that impale soft-bodied prey with surgical precision. Either way, the mechanics are the same. An internal spring-loaded structure called a saddle stores elastic energy, released in an instant when the shrimp contracts its muscles. The result is an acceleration so fast that the surrounding water boils, literally. This boiling phenomenon, known as cavitation, creates a vapor bubble that collapses with explosive force. The collapse produces a brief flash of light and a secondary shockwave powerful enough to kill prey, even if the initial strike misses. It is one of the few times in nature where light is generated not by chemistry or bioluminescence, but by physics, the energy of destruction manifesting as a momentary spark. A shell that survives the first hit may still shatter from the invisible follow-up. For creatures like crabs and snails, which depend on armor for protection, the mantis shrimp represents the ultimate evolutionary checkmate, a predator that doesn't need to pierce defenses because it erases them. Yet, for all its raw power, the mantis shrimp does not strike carelessly. Within its burrow, it conducts ritualized confrontations designed to prevent unnecessary injury. When two individuals compete for territory or mates, they first engage in posturing, raising their claws, spreading appendages, and flashing polarized patterns that signal strength. These contests are carefully calibrated. Each shrimp assesses the other's size and stamina before deciding whether to escalate. In many cases, the dispute ends without violence. Even for a creature built for impact, the risk of mutual damage is too great. The clubs are not indestructible. Repeated strikes can fracture the appendages, rendering them useless for both hunting and defense. It is a rare example of restraint from an animal whose evolutionary design screams aggression, a living paradox where control is as important as capability. From a biomechanical standpoint, the mantis shrimp's strike is a marvel of natural engineering. The spring mechanism operates like a bow and arrow. Tension accumulates as the shrimp flexes a saddle-shaped structure made of chitin and mineralized calcium phosphate. When released, the stored energy converts to motion in less than a millisecond. Researchers have calculated that the force exerted by a large peacock mantis shrimp could, if scaled to human size, equal the energy of a car crash. The speed is so extreme that it challenges the limits of biological material. To survive its own weapon, the shrimp's limbs are reinforced with a herringbone-patterned microstructure that dissipates stress waves through layered composites. Engineers now study this design for inspiration in building stronger synthetic armor and ceramics. The ecology of the mantis shrimp reflects its weaponized anatomy. Burrowed into sandy flats, coral rubble, or rocky crevices, it builds fortresses, sometimes multiple entrances leading to an interior chamber lined with shell fragments. From this base, it launches ambushes with surgical timing. Smashers target crabs, mollusks, and even other crustaceans, while spearers specialize in fish. Their hunting strategy is a fusion of patience and violence. The shrimp remains motionless, body half concealed, until prey ventures within range. Then, a flash. One strike, one kill. The efficiency is staggering. Unlike most predators that must chase or grapple, the mantis shrimp wins by instantaneous certainty. But the story of its life is not only about killing. Mantis shrimp are also among the most socially complex invertebrates known. Many species form long-term monogamous pairs, sharing burrows and jointly caring for eggs. The female broods the clutch, keeping it aerated and free of parasites, while the male hunts and brings food. Communication between partners continues through visual signals and antennal contact, a delicate domestic life built beneath the shadow of overwhelming power. In ecosystems where predation is constant and competition fierce, such cooperation provides rare stability. The mating rituals themselves showcase the same intricate balance between aggression and restraint. Courtship often begins with visual display. The male flashes polarized signals along his body and waves his appendages in controlled arcs, demonstrating health and vitality. The female responds with reciprocal flashes or subtle posture changes. These exchanges are not just for attraction, but for assessment. The ability to produce strong polarized reflections indicates a well-maintained exoskeleton, free of damage or parasites, an evolutionary advertisement of genetic fitness. Even their sense of vision plays a role in navigation and orientation within the reef. The mantis shrimp's eyes move independently, each capable of tracking separate objects, yet they can also converge for depth perception far superior to that of most animals. Some studies suggest they use polarized light to locate burrows or to read the reflective patterns of the ocean surface for orientation. This sensory capability grants them near-perfect awareness of both prey and predator, an advantage critical in the crowded, competitive environment of the reef floor. Predators of mantis shrimp are few and for good reason. Moray eels, groupers and octopuses occasionally manage to capture one, but often at a cost. A single misjudged strike can leave the attacker with a broken jaw or tentacle. Most learn to avoid the telltale shape of the shrimp's burrow, the narrow entrance ringed by fragments of shattered shells, like the warning signs of a minefield. Those that persist are sometimes met with the sound that defines this creature's mythos, a sharp, percussive crack that echoes underwater like a miniature gunshot. To divers who have heard it, the sound carries both fascination and unease, the reef's reminder that size does not determine danger. The mantis shrimp's world extends beyond violence into the frontier of sensory evolution. Its visual system may hold the key to understanding how animals perceive reality itself. Scientists studying the shrimp's ability to detect circularly polarized light have found that it can distinguish reflections from transparent surfaces, an ability useful for spotting the scales of camouflaged fish or the glint of a predator's eye. Some species even use circular polarization in their courtship patterns, encoding messages in a spectrum humans cannot see. It's a biological encryption system running parallel to the visible world, a secret conversation of light beneath the waves. In ecological terms, the mantis shrimp acts as both predator and engineer. Its burrowing reshapes sediment layers, aerating the substrate and influencing nutrient cycles. The fragments left behind from shattered shells enrich the calcium carbonate composition of the reef, subtly contributing to its long-term stability. What appears as destruction in the moment becomes construction over time, a recurring theme in ocean ecology where every act of predation feeds into the system's renewal. To witness the mantis shrimp hunt is to glimpse the edge of possibility in evolution, an animal so specialized that it borders on mechanical perfection, yet still governed by instinct and restraint. In the shallow blue light, one emerges from its burrow, claws half raised, eyes pivoting like periscopes. A crab scuttles nearby, oblivious. The shrimp tenses. For a fraction of a heartbeat, the reef seems to freeze. Then a flash, a bubble, a crack, a burst of light, and the water swirls with fragments of shell. The mantis shrimp withdraws, meal in tow, vanishing back into its tunnel as the dust settles. It leaves behind no lingering presence, no ripples of warning. only a memory of the invisible signal that preceded the strike and the visible aftermath that followed. In the mantis shrimp's world, the unseen governs the scene, and every flash of light is a conversation between life and death, broadcast in colors only it can understand. The reef at dawn hums with the soft percussion of waves breaking overhead, each surge sending a shiver of light through the water. Small fish hover in the warm currents, their scales refracting sunrise into drifting sparks. Beneath this radiant calm, shadows stir in the coral labyrinth, long, sinuous, deliberate. The moray eel slides from its crevice like liquid muscle, a body without edges, skin glistening with the subtle sheen of mucus that protects it from abrasion. It does not swim so much as it flows, a ribbon of intent gliding through narrow passageways where even light struggles to follow. The reef is a maze, but for the moray it is home, a terrain mapped by scent and memory, where every hole is a potential ambush point and every crevice a locked door it alone knows how to open. For most of the day, the moray remains hidden, its head protruding from the coral with jaws half open in a perpetual snarl. To the casual observer, this expression suggests menace, but the open mouth is not aggression, it is respiration. Unlike most fish, morays lack the pumping mechanism that moves water over the gills. Instead, they must continuously open and close their mouths to breathe, a rhythmic cycle that, in the filtered light of the reef, looks like quiet warning. This constant motion, paired with glassy eyes and exposed teeth, has earned the moray its reputation as a sinister presence. Yet beneath that intimidating facade is an animal of surprising precision and intelligence, one that plays a critical role in the reef's social network of predators. When night deepens and the plankton clouds bloom, the moray becomes fully alive. It leaves the safety of its burrow, muscles coiling and uncoiling like springs under wet silk. Its sense of smell, amplified by tubular nostrils, leads the way through darkness. Unlike the fast-moving hunters of open water, the moray is built for confined pursuit. Its elongated, boneless body can slip through gaps that would trap any other predator, and its skin, thick, scaleless, and coated in protective mucus, allows it to grind against coral and rock without injury. This adaptation makes the eel a specialist in what might be called structural predation, the art of killing inside the architecture of the reef. But even such mastery has limits. Many reef fish are equally adept at hiding, using the same maze of tunnels and overhangs to evade pursuit. The moray's elongated body can reach them, but its range of vision is poor, and its strike relies on ambush rather than chase. Evolution's answer to this problem did not come through anatomy, but through alliance. The moray eel learned to hunt in partnership, and its most famous collaborator is the grouper. In the clear shallows of the Red Sea, a dusky grouper hovers above a coral head, fins fanning slowly as it scans the terrain below. A few meters away, a moray eel protrudes from its den, nostrils twitching at the scent of prey. Then, the grouper turns toward the eel and performs a distinct, deliberate motion, a rapid head shake, directed not at the reef, but at its potential partner. This is the signal. It means come with me, there is work to be done. The grouper cannot speak, but the motion is unmistakable. Incredibly, the moray recognizes it. The eel emerges, sinuous and alert, and together they glide across the coral landscape toward a shared target. This partnership is one of the most remarkable examples of interspecies cooperation in the animal kingdom. A collaboration based not on instinct alone, but on communication and role specialization. The grouper is the scout and enforcer. Its large eyes and quick bursts of acceleration make it ideal for locating prey in open water. But once that prey hides among the coral, the grouper's bulk becomes a disadvantage. The moray, on the other hand, is the locksmith, the infiltrator capable of entering the labyrinth where the grouper cannot follow. Together they form a two-part hunting machine, perfectly adapted to the geometry of the reef. The sequence unfolds with astonishing coordination. The grouper patrols the coral surface, scanning for movement. When it spots a fish darting into a crevice, it positions itself at one exit, body rigid, blocking escape. The moray then threads its way into another entrance, its slender body writhing through the coral's interior tunnels. For the prey, perhaps a wrasse or a squirrelfish, the trap is perfect. In trying to flee one predator, it drives itself into the jaws of the other. The result is swift, precise, and almost surgical. Both hunters then share the meal, each taking turns or claiming separate pieces depending on the size of the catch. The efficiency of this alliance is so high that studies have shown groupers actively seek out specific morays when hunting, remembering individual partners and signaling them repeatedly over time. What makes this relationship extraordinary is the level of cognition it implies. Cooperative hunting across species requires more than instinct. It demands communication, trust, and a mutual understanding of cause and effect. The grouper's headshake signal, often repeated near the moray's hiding place, is not a random display, but an intentional invitation. The moray responds only when it is hungry, ignoring the signal otherwise. During hunts, both predators adjust their behavior based on the other's position, even switching roles if necessary. In laboratory experiments, groupers have been observed recruiting eels by swimming directly to their hiding spots and performing the same headshake motion until the eel emerges. The two then move together side by side across the reef, the fish leading in open areas, the eel taking over in narrow spaces. It is the underwater equivalent of a tactical partnership. This cooperative dynamic is built on evolutionarily complementary strengths. The grouper's advantage lies in power and visibility. It commands space in the open, using its speed to intimidate and corner. The moray's advantage lies in precision and access. It converts hidden territory into hunting ground. Together they turn the reef's complex architecture, which for most predators is a barrier, into a weapon. The coral, riddled with passageways and chambers, becomes a labyrinthine trap where prey loses not only speed but certainty. The grouper's shadow above triggers panic. The eel's arrival below removes every exit. And in a moment that would seem almost unfair were it not so brilliantly evolved, the prey chooses its own death. To watch a hunt from the prey's perspective is to experience pure confusion. A small parrotfish darts into a coral hollow, panting through gills as it presses against the inner wall. It believes itself safe. Predators rarely enter such spaces. But then, a shape appears at the far end of the tunnel, long and slender, advancing with deliberate grace. The eel's head moves side to side, taste-testing the current with its twin nasal tubes. The parrotfish reverses direction, fleeing toward the open exit, only to find the grouper's massive jaws waiting, motionless, just beyond the light. There is no struggle, only inevitability. The coral maze, which once promised safety, becomes the perfect architecture of entrapment. Even outside this iconic partnership, the moray's predatory adaptations are formidable. Its jaws operate on a dual system unique among bony fish. When it seizes prey, a second pair of jaws, the pharyngeal jaws, shoot forward from its throat to grip and drag the victim deeper into the mouth. This mechanism, reminiscent of the fictional xenomorph from human cinema, allows the eel to swallow prey without relying on suction or body recoil. In tight spaces where leverage is limited, this adaptation ensures a kill even when there is no room to maneuver. The entire feeding process happens with mechanical precision, muscles contracting in a wave that moves food smoothly down the digestive tract. Beyond hunting, the moray's biology reflects its specialization for confined living. Its skin secretes a thick mucus that replaces scales, protecting against abrasion and infection. Some species even use this slime to coat their tunnels, making their movement more efficient, a form of biological lubrication. Their eyesight, though poor, is compensated by acute chemosensory ability. They taste the water for traces of amino acids and scent molecules left by passing prey. Combined with their flexible skeletal design, reduced bone structure and extended vertebral columns, these traits make the moray eel one of the most capable navigators of reef interiors. The relationship between moray and grouper is not unique in principle, but rare in complexity. Other species engage in opportunistic cooperation, dolphins driving fish toward fishermen, or crocodiles sharing kills with herons. Yet few demonstrate such refined coordination or repeated communication. It suggests that the boundary between instinct and intelligence in the ocean is more porous than we once believed. Here, Evolution did not just shape anatomy, but engineered behavior. The ability to recognize another species not as competition, but as an ally. And the benefits extend beyond the hunters themselves. By regulating populations of smaller reef fish, the Grouper Moray alliance indirectly maintains coral health. Without these predators, herbivorous fish would overgraze or overpopulate, disrupting the balance of algae and coral growth. In this way, a partnership born from hunger sustains the broader ecosystem. Even the act of hunting through coral channels stirs sediments, redistributing nutrients and oxygen within the reef. The moray's movements, threading through stone like veins in a living body, keep the reef's metabolism active. As the sun climbs higher, the water brightens to turquoise, and the coral maze begins to glow with refracted light. The moray retreats to its den, curling into the cool shade of a coral crack. The grouper drifts nearby, hovering with slow, rhythmic fin beats. The hunt is over, but the partnership endures, one built not on loyalty, but on evolutionary pragmatism. When hunger returns, the grouper will come again, shaking its head in silent invitation. The moray will emerge, slipping from shadow to service, the locksmith unlocking yet another door in the reef's endless labyrinth. Together, they turn architecture into strategy, instinct into cooperation, and survival into art. Beneath the calm surface of the coral world, this ancient alliance continues, proof that in the ocean, even the most unlikely neighbors can learn to share the same key. In the late morning light of the tropics, the open water near the reef flashes with molten silver. Sunbeams pour through the surface, fractured by each wave, scattering into shifting columns that ripple down toward the blue. For a moment it seems that nothing larger than a sardine moves within this gleaming mosaic. Then, one of the shafts of light flickers in an unusual way, a subtle distortion, a hesitation in the flow of brightness, and what appeared to be a reflection resolves into a form. Long, lean, and almost invisible, a barracuda drifts just beyond the range of attention. It is both there and not there, suspended in the mid-water haze like a piece of the sea that learned to think. The barracuda is the ocean's optical illusionist. Its entire existence is built on mastering the physics of light. Its flanks are plated in guanine crystals, microscopic reflectors embedded in the skin that act as near-perfect mirrors. These scales don't shimmer like a normal fish's do. Instead, they erase the animal's outline by matching the intensity and angle of surrounding light. To the human eye and to most prey, the barracuda doesn't gleam so much as vanish. Its body becomes a continuation of the water itself, a chrome spectre woven into the play of sun and current. This is not camouflage in the sense of mimicry or color change. It is optical physics weaponized. In the right conditions, even the shadow it casts dissolves into the glare. Its body design complements the illusion. Long and cylindrical, with a sharply tapered head and large, forward-facing eyes, the barracuda is an evolutionary study in minimal drag and maximum acceleration. Its muscles are arranged in a double helix of fast-twitch fibers that can contract with explosive force, while its jaw, armed with serrated teeth angled backward, can open nearly one-third of its body height in a single snap. Yet it spends most of its time completely motionless, conserving energy while allowing its disguise to work. It doesn't need to hide behind coral or vegetation. Its camouflage functions in open water, where most animals are exposed. The effectiveness of this design depends on the sun. In bright conditions, light refracts from the surface in lines that stretch downward like ghostly ladders. Each column shifts with every ripple, creating a dynamic patchwork of brightness and shadow. The barracuda aligns itself precisely with these glare lines, maintaining an orientation that keeps its reflective skin matched to the pattern. From below, it blends with the silver of the surface. From above, its darker dorsal shade matches the depths. From the side, it mirrors the gradient of the sea itself. Prey fish scanning for threats see only distortion, the shimmer of sunlight through water, not the outline of death approaching. When the moment to strike comes, the transformation is instantaneous. A single flex of the tail propels the barracuda forward with explosive speed, nearly 50 kilometers per hour in a short burst, fast enough to leave a visible shockwave of disturbed water behind it. Its attack is not a chase but a lunge, a weaponized ambush that unfolds in milliseconds. It targets not the slow or the weak, but the disoriented. Individuals that stray just slightly from the group, whose reaction times are a fraction too late. The barracuda's strategy relies not on endurance but on geometry. It attacks through the lines of light that conceal it, using the glare as both shield and guide. In the open sea, light is not merely illumination, it is terrain. The physics of visibility dictates survival. Many fish rely on countershading to remain undetected, dark backs, pale bellies, blending into the gradient. The barracuda has evolved beyond that basic principle. Its mirror flanks adapt to every subtle shift in brightness, creating an active, continuous camouflage. The underlying muscles can even fine-tune the angle of scales to adjust reflection, a form of dynamic blending far more sophisticated than static coloration. This adaptation gives the predator control over its invisibility, allowing it to move freely in the most exposed environments without being seen. But the barracuda's tactics extend beyond ambush. In the open pelagic zones where schools of small fish gather for safety, the barracuda employs a second strategy: psychological warfare through precision movement. It doesn't attack the center of a school. Instead, it shadows the perimeter, maintaining just enough distance to induce subtle tension among the fish. The school senses danger, but cannot locate its source. The collective formation begins to waver. Individuals at the edge drift out of alignment, splitting the group's symmetry. The barracuda then accelerates, slicing through the fragmented edge, isolating one or two victims before the school can reform. This shadow-stalking behavior is not random. It's a deliberate manipulation of schooling dynamics, a predator's understanding of collective psychology. Schools rely on synchronized motion to confuse attackers. Each fish mirrors its neighbor's direction within fractions of a second, creating an ever-shifting wall of bodies that disorients predators. The barracuda undermines this defense by exploiting the lag between individual responses. By hovering motionless in parallel with the group, it introduces false cues. Its shape mimics the direction of the school's flow. When it finally lunges, the movement triggers a cascade of misinterpretations among the prey. The school collapses into chaos, and the predator harvests opportunity from confusion. Its predation style reflects an ecological role similar to that of wolves or big cats: selective pressure. By targeting disoriented or diseased individuals, barracudas help maintain the health and cohesion of prey populations. The presence of a barracuda alters behavior across entire ecosystems. Small fish feed closer to cover, plankton grazers tighten their formations, and even other predators, smaller jacks or snappers, adjust their hunting routes to avoid crossing its path. The barracuda is not merely a participant in the reef's web of life, it is an enforcer of discipline, shaping how other animals move, feed, and survive. Its sensory adaptations are equally fine-tuned for its niche. The eyes, proportionally large, are designed for high-speed tracking in bright, high-contrast environments. They contain specialized cone cells that detect rapid motion without distortion, an ability to process flickering light that would blind or dazzle less adapted species. The lateral line, a system of pressure-sensitive cells running the length of the body, acts as an underwater radar, detecting the slightest disturbances in nearby water. Together, these senses form an integrated targeting system, allowing the barracuda to locate prey by soundless vibration even when visual cues are misleading. Though primarily solitary, barracudas sometimes assemble in loose groups, especially in deeper channels or around reef drop-offs. These aggregations, often mistaken for schooling behavior, are more accurately described as temporary truces, individuals aligning along current lines for hunting efficiency rather than social cooperation. Within such gatherings, a hierarchy forms subtly through posture and spacing. The largest individuals, sometimes exceeding 2 meters in length, take the prime positions along the current's edge where incoming prey is most likely to appear. Smaller ones hold back, waiting for scraps or opportunities in the wake of a larger strike. The result is a silent, ordered assembly of mirrored blades suspended in blue emptiness, each reflecting light and each invisible to the others. Their feeding habits extend beyond live prey. A barracuda's scavenging instinct often brings it close to human activity. In some tropical shallows, divers report the unsettling experience of being followed by a single, motionless fish, hovering just beyond reach, its mirrored sides catching flashes of light. It isn't aggression, it is curiosity, driven by the animal's attraction to the glint of metal or the shimmer of bubbles, which mimic the signals of prey. To many observers, the barracuda's gaze feels uncomfortably intelligent, an unblinking stare that measures motion and intention. Yet this behavior underscores the same evolutionary principle that defines its life, vision as both weapon and defense. In the ecological chain, the barracuda occupies a transitional niche between reef and open ocean, acting as a bridge predator. It hunts near coral edges, but patrols the pelagic shallows, where it regulates populations of mid-water fish that migrate between habitats. Its role maintains the balance between the productivity of reefs and the nutrient flows of the open sea. When populations decline, often due to overfishing, smaller predatory fish multiply unchecked, destabilizing food webs. In this sense, the barracuda's presence is not a threat to biodiversity, but a guarantor of it. Evolution has left few wasted features on its body. Its teeth, sharp and uneven, are shaped to cut rather than crush. The jaw closes with such speed and precision that many prey are sliced in half before they can react. Each tooth is slightly curved backward, preventing escape once contact is made. Despite this ferocity, barracudas rarely bite without purpose. Accidents involving humans, while occasionally sensationalized, are almost always the result of mistaken identity. A glinting object, mistaken for fish under the glare of the sun. The predator's world is governed by light and reflection, not malice. As midday fades, the water's surface burns with brightness, and the barracuda drifts upward, aligning perfectly with the blinding glare. Its chrome flanks vanish once more into invisibility. Below, a school of fusiliers passes, unaware that one of the sunbeams above is alive and waiting. The predator's body tenses. The tail flicks once. The silver streak explodes downward, cutting through the glare like a thrown knife. A single fish disappears from the formation. The rest scatter, then regroup, formation restored, equilibrium reasserted. The barracuda circles once, then glides back into the shimmer, leaving behind only disturbed bubbles and light. In the silence that follows, the water seems empty again. Yet the illusion persists. Somewhere within the shifting lattice of sunshafts, the mirror ghost still waits, invisible against the brightness it commands. The ocean hides nothing from it, and yet it hides completely within the ocean. Among all predators of the reef, none embodies light and shadow so completely. The hunter that kills by vanishing, the spectre that turns visibility itself into its most perfect disguise. The morning sun over the Gulf shallows filters through calm, brackish water, transforming the surface into a mirror of soft gold. Beneath it, shadows move with practiced unity, a pod of bottlenose dolphins advancing across the flats. The air is still, the tide low, and the water so shallow that even a fish's escape route is limited to a few frantic meters. The dolphins know this. They have hunted here countless times, refining a strategy that is as much performance as predation. In the coming minutes, the calm water will erupt into chaos, yet not from brute speed or random pursuit. The dolphins will win by deception. What looks like play to the untrained eye is actually choreography. A collective illusion staged with intelligence so sharp it manipulates the very behavior of their prey. The lead dolphin begins by circling a small school of mullet, moving deliberately and steady, tail sweeping close to the seabed. As it turns, the motion stirs up a curtain of silt, fine sediment rising in thick, opaque spirals. Within moments, the water transforms into a cloudy ring, an expanding wall that seems solid to the panicked fish inside. The dolphins know it is only mud, a temporary illusion, but to the mullet, it is a deadly barrier. Their instincts tell them to flee from dark shapes and opaque water, to bolt toward the light. That is precisely where the trap is set. The circle closes. On cue, one or two dolphins accelerate through the only clear opening, driving the fish upward in a synchronized burst. The mullet leap, desperate to escape the false wall. Waiting mouths snap them from the air in arcs of sunlight and spray. What began as physics, the mere suspension of silt, becomes psychology. The dolphins have turned mud and fear into tools, crafting a predator's mirage that needs no net, no teeth, only understanding. This behavior, known as mud-ring feeding, is a testament to the dolphin's cognitive depth. Each movement in the circle is coordinated, not random. The lead dolphin, often the oldest female, initiates the rotation, while others position themselves to strike. The group relies on a combination of visual cues and acoustic signals, short burst pulses and whistles that convey timing and direction. These are not simple alarms or calls of excitement. They are structured communication, patterns of sound that vary subtly in frequency and rhythm depending on context. In laboratory settings, similar whistle sequences have been shown to function almost like names or labels, identifying individual dolphins within the group. In the wild, this vocal flexibility allows them to update their tactics in real time, adjusting formation, assigning attack roles, and shifting strategy mid-hunt. Such precision would be extraordinary in any social species, but dolphins have taken cooperation to a level approaching tactical planning. Their brain-to-body ratio rivals that of great apes, and the neocortex, the part associated with reasoning and sensory integration, is highly convoluted, indicating complex processing capacity. Yet what truly defines their intelligence is not just memory or perception, but coordination. They think as a unit. Every individual in the pod participates in shared decision-making, responding to others' cues faster than conscious thought would allow in humans. This phenomenon, known as emergent cognition, means that the group's collective mind can solve problems no single dolphin could manage alone. Nowhere is this more striking than in the behavior known as strand feeding, a risky maneuver seen along certain coastal regions of the southeastern United States. The strategy begins as the tide recedes. A pod patrols the shallows near mudflats or riverbanks, herding schools of fish toward the shoreline. Then, in a coordinated burst, the dolphins accelerate, not to kill but to deceive. They drive the fish ahead of them until panic forces the prey to leap onto the mud. In an instant, the dolphins launch themselves partially out of the water, stranding on their sides as they seize the floundering fish. Within seconds, they wriggle backward into deeper water, ready to repeat the act. The brilliance of strand feeding lies in its risk. Every participant must calculate distance, angle, and speed with precision. Too early, and the fish escape back into the channel. Too late, and the dolphin risks injury or entrapment on the shore. Yet they execute this maneuver flawlessly, over and over, adjusting to tides and terrain. Even more remarkable, young dolphins learn this technique through observation, not instinct. Mothers teach by demonstration, repeating the act until calves attempt it themselves. This cultural transmission, knowledge passed not genetically but socially, elevates dolphins from merely intelligent animals to cultural beings. Both mud-ring feeding and strand hunting reveal a deeper pattern, deception as a tool of survival. While many predators rely on camouflage or stealth, dolphins manipulate perception itself. Their success depends not only on physical power, but on their ability to shape how other creatures interpret the world. This cognitive manipulation is mirrored in their own communication systems. Within a pod, dolphins maintain constant acoustic dialogue, a complex blend of whistles, clicks, and low-frequency bursts. Some sounds are used for echolocation, bouncing off objects to map the environment. Others are social signals that organize the group. But beyond these known categories lies a spectrum of behavior researchers are only beginning to decode. During hunts, dolphins produce distinct whistle exchanges that seem to assign roles, one tone indicating a driver, another a blocker, another a catcher. These signals can change mid-pursuit, allowing the pod to adapt instantaneously to the movements of prey. In essence, they can reassign positions on the fly, like a team altering its formation in the middle of play, only underwater, and at speeds that make human coordination look primitive. This adaptability also extends to alliances beyond hunting. In some populations, male dolphins form long-term coalitions, pairs or trios that cooperate to court females or defend territories. These alliances last for decades, requiring stable memory and social awareness. Each dolphin must recognize dozens of individuals by their unique signature whistle, a kind of vocal fingerprint learned early in life. They use these acoustic identifiers to maintain relationships across time and distance, even greeting old companions after years apart with precise whistle mimics, the marine equivalent of calling someone by name. What makes these interactions even more fascinating is their acoustic subtlety. Dolphins can whistle through their blowholes while simultaneously emitting echolocation clicks, effectively speaking and seeing at the same time. In a feeding context, this dual-channel communication means a dolphin can coordinate with a partner while actively scanning prey with sonar. The two systems, social and sensory, operate in tandem, forming a kind of parallel processing unmatched in the animal kingdom. The result is both efficiency and adaptability. When one dolphin's role changes mid-hunt, the pod adjusts instantly, guided by a combination of sound and intuition. Beyond their intellect, dolphins are also physical marvels of hydrodynamic engineering. Their streamlined bodies minimize drag, and their musculature allows for bursts of speed exceeding 30 kilometers per hour. During group hunts, they exploit the physics of wave riding, synchronizing with each other's wakes to conserve energy. Some hunts become endurance games, where dolphins corral large schools for extended periods, taking turns chasing and feeding while others recover. This rotation mirrors the cooperative hunting of wolves or lions, but executed in 3 dimensions and through sound. Ecologically, these predators serve as both regulators and architects. By controlling fish populations, they influence the balance of coastal ecosystems, indirectly shaping the health of seagrass beds and coral structures. Their hunting activity stirs sediments, redistributing nutrients through the water column and stimulating plankton growth. Even their waste contributes to marine nutrient cycles, connecting surface ecosystems to the deep through organic matter exchange. In short, every deception and every hunt ripples outward into the functioning of the entire habitat. There is irony, too, in their mastery of illusion. Humans for centuries have romanticized dolphins as benevolent, playful companions of the sea, a myth that mirrors their deceptive grace. But the truth is more complex and far more interesting. They are neither saints nor simpletons. They are strategists. Their intelligence evolved not for art or morality, but for competition, social maneuvering, and survival in a landscape of constant negotiation. The smiles we perceive are artifacts of anatomy, not emotion, though genuine emotion, joy, curiosity, even frustration, exists beneath the surface. They are predators with empathy, opportunists with community. As the sun rises higher, the pod in the shallows finishes its hunt. The silt cloud disperses, the water clears, and the evidence of their deception fades as quickly as it formed. The dolphins regroup in loose formation, their movements casual now, the tension of the chase replaced by the rhythmic calm of travel. Below them, scattered mullet scales glint in the light, drifting down like remnants of a shattered illusion. For the observer, it is hard not to feel awe at the perfection of the act. The dolphin's world is one of strategy and signal, of knowing when to reveal and when to hide. Their walls are not built from stone or coral, but from understanding, barriers of perception shaped by intelligence. In every murky ring of mud, in every feigned retreat or coordinated surge, they remind us that deception is not only the domain of humans. In the ocean, truth itself is just another current to be mastered. The Southern Ocean is calm this morning, a deceptive calm, broken only by the slow heave of grey swells and the rhythm of sea ice grinding at the edge of an Antarctic bay. The horizon glows pale with the promise of another short, frigid day, and the only visible movement comes from the scattering of penguins and seals resting along the floes. To the eye, it seems peaceful, almost static. But beneath the ice, beneath the skin of the sea, something else moves, coordinated, silent, calculating. The orcas have arrived. The killer whale, or Sinus orca, is both myth and mechanism, a mammal so intelligent that its hunting strategies border on choreography, and so physically refined that it can manipulate the ocean's physics to deceive both prey and perception itself. Its brain, proportionally larger than that of nearly any other marine predator, is mapped for social memory and acoustic precision. Its body is built for control, dense muscle, tapered fins, and a tail that can deliver acceleration with the efficiency of a hydrofoil. But its most powerful tool is not strength or speed, it is understanding. Orcas are strategists of water and sound. They have turned physics itself into a weapon, a con that plays out in the space between illusion and force. In the cold southern bays of Antarctica, the deception begins with the surf. Weddell seals haul themselves onto floating ice sheets, confident that the solid platform shields them from what lurks below. They are wrong. A small pod of orcas assembles just beneath the surface, perfectly aligned, 5 bodies in a straight line, noses inches apart. Each exhales a plume of bubbles, releasing a faint hiss that merges with the ambient sound of the sea. Then, with a synchronized flick of their tails, they surge forward, generating a rising pressure wave. The motion displaces water upward, sending a swell racing toward the ice. The wave hits the floe, cracks it at the edges, and floods its surface with cold seawater. The seal, panicked, scrambles backward, but the next wave comes, larger and faster. The ice tilts, fractures, and finally breaks apart, sliding its terrified passenger into the waiting jaws below. This tactic, known as wave washing, is one of the most spectacular examples of cooperative hunting in the marine world. It requires not only synchronization but physics-level intuition. Each orca in the pod must adjust its speed and depth to generate the correct interference pattern for maximum force at the right moment. Too early and the wave dissipates. Too late and the ice stabilizes. These calculations occur instinctively, learned through years of practice and refined through observation. Younger orcas in the group trail behind, watching, memorizing. In later hunts, they will attempt smaller waves, testing the timing, failing often, and being corrected by older members with subtle body cues and vocal clicks. In these lessons, the ocean becomes a classroom and physics the curriculum. Yet the orca's mastery of illusion extends far beyond waves. The species' greatest con involves the control of sound itself, a deliberate manipulation of one of the ocean's most fundamental properties. Orcas navigate and hunt primarily through echolocation, emitting a series of high-frequency clicks that bounce off nearby objects and return as echoes. This biological sonar paints an acoustic map of their surroundings with astonishing resolution, a 3-dimensional picture rendered entirely in sound. But in certain hunts, orcas silence this ability on purpose. When stalking prey capable of detecting or evading sonar, such as seals or even other cetaceans, orcas enter what researchers call silent mode. They cease echolocation entirely, cutting themselves off from their main sensory input. Instead, they rely on low-frequency listening, passive acoustics, and visual cues. It is a paradoxical tactic, choosing temporary sensory blindness to become invisible to others. Many marine mammals can detect the high-frequency bursts of active sonar, associating the sound with danger. By staying silent, orcas erase their acoustic presence, vanishing from the prey's perception. It is as though they become a shadow in the sea, unseen and unheard until it is too late. This technique demonstrates a kind of intelligence rarely observed in the wild, metacognition, or awareness of one's own sensory systems. To suppress sonar deliberately means understanding not only how sound reveals, but how it betrays. The orca's brain, with its extensive paralimbic lobes, supports this capacity for sensory manipulation. It can shift from active to passive perception with precision, effectively changing the physics of its interaction with the environment. Some pods use silence in stages, alternating between echolocating scouts and passive ambushers. In these hunts, the pod behaves like a single organism, one half emitting information, the other half absorbing it. The sophistication of this acoustic control extends into communication. Orcas are divided into cultural populations, known as ecotypes, each with distinct dialects, acoustic languages that encode identity, kinship, and territory. Within a single pod, these calls are shared across generations and maintained with remarkable fidelity, even after decades. Some vocalizations are used for coordination during hunts, others for navigation in thick ice or murky waters. The diversity of dialects is so precise that scientists can identify an orca's family lineage by sound alone. These dialects act as cultural signatures, marking one group's identity much like language defines human societies. Beyond cooperation, orcas also practice imitation and rehearsal, behaviors rarely seen outside humans and great apes. In the calm waters off Norway, pods have been observed engaging in training hunts, using floating debris or kelp as stand-ins for live prey. Adults take turns demonstrating techniques, stealth approaches, ambush angles, and team coordination, while juveniles mimic the maneuvers. In some cases, they even appear to role-play a full hunt, complete with the silent approach, coordinated dive, and mock capture. The purpose is clear: refinement through repetition. These training dummies are not random playthings but learning tools. They allow the next generation to practice precision without risk or waste. In these sessions, the older females, the matriarchs, serve as instructors. Their role in orca society cannot be overstated. Unlike most marine mammals, orca females live long after reproduction, often exceeding 80 years. Their extended lifespan serves an evolutionary purpose: knowledge retention. Matriarchs carry the collective memory of migration routes, seasonal prey movements, and safe calving grounds. They remember where to find herring shoals when ocean currents shift, or how to navigate ice barriers that change yearly. This knowledge, passed through decades of experience, is critical to the survival of the entire pod. The training hunts therefore serve not only as education for the young, but as rehearsal for the collective, a way of preserving culture in a changing sea. The global distribution of orcas reflects this cultural adaptability. Different populations have evolved distinct hunting specializations shaped by local ecosystems. In Patagonia, orcas intentionally beach themselves to snatch sea lion pups from the surf, a technique that demands perfect timing and bodily control to avoid stranding. In the Pacific Northwest, resident pods feed almost exclusively on fish, using acoustic calls that are calm and rhythmic, suited for coordinated chases. Transient pods in the same waters, which hunt marine mammals, operate in silence, communicating only with subtle body movements. Even within a single species, behavior diverges so dramatically that some scientists argue these populations represent distinct subspecies defined by culture rather than genetics. At the core of all these adaptations lies the orca's ability to model reality. It manipulates the ocean not through instinct alone, but through understanding, a grasp of cause and effect that verges on abstract reasoning. When generating waves, it anticipates the behavior of water. When silencing sonar, it predicts how sound travels through the sea. When training its young, it reconstructs entire hunts as simulations. In every case, the orca exploits physical laws as if they were tools, rewriting them to suit its purpose. Ecologically, this mastery positions the orca as an apex regulator. Its predation patterns influence populations from penguins to whales, shaping marine communities across the globe. In the Arctic, the arrival of orcas has driven seals and narwhals to retreat into shallower, ice-packed refuges, altering migration routes and feeding grounds. In tropical seas, their selective pressure on tuna schools maintains balance between mid-level predators and plankton populations. Even scavengers benefit. The remains of orca kills feed sharks, seabirds, and benthic communities, redistributing energy through the food web. The orca is not merely a predator, it is an ecological architect. And yet, for all its dominance, the orca is not invincible. Its intelligence, so finely tuned to pattern and precision, makes it vulnerable to the disruptions humans impose. Noise pollution from shipping and sonar interferes with communication, fragmenting pods that rely on sound to coordinate. Declines in key prey, like herring and salmon, erode traditional hunting knowledge, cultural wisdom built over centuries of experience. Some matrilines have vanished entirely, leaving behind orphaned calls that echo in empty waters, the ghosts of dialects no longer understood. Still, the orca endures. Its adaptability is its armor, and its understanding of the physical world ensures that wherever the ocean changes, it will find new ways to manipulate it. On a calm afternoon in the Ross Sea, a pod surfaces near a sheet of ice, their black and white bodies cutting through the grey water like punctuation marks in motion. They exhale in bursts of mist, regroup, and dive again beneath the flow. Moments later, the surface begins to tremble. A wave forms, small at first, then gathering height. The ice tilts, and another seal's illusion of safety dissolves. Beneath the surface, the pod regroups, sharing clicks and low moans that echo through the cold expanse. The hunt is over, but the lesson endures, a fluid exercise in power, precision, and knowledge. The orcas vanish into deeper water, their voices fading into distance. Behind them, the ice resettles, as if nothing happened. The ocean returns to stillness, concealing the brilliance that moves unseen below. The Pacific night is heavy and metallic, thick with suspended life and the scent of slow death. Along a coral atoll where the sea deepens abruptly, a shadow moves just below the moonlit surface, wide-headed, slow, unhurried, yet with every sweep of its tail, a precise reading of the ocean's invisible language. The tiger shark, Galiocerdo cuvier, glides through the dark like a mind moving through memory. To the untrained eye, it seems aimless, wandering, but to the shark, every molecule of water is information. It is not hunting in the way other predators chase. It is reading, scanning the chemical paragraphs of the sea for traces of suffering, decay, or opportunity. The tiger shark's world is not governed by sight or sound, but by gradients of chemistry and vibration. Along its snout, hundreds of tiny pores, the ampullae of Lorenzini, detect electrical fields produced by living cells. Each pore is filled with a conductive gel that can sense voltage changes as faint as a few billionths of a volt, allowing the shark to perceive the faint electric rhythm of a heartbeat buried under sand, or the fading pulse of a dying fish far away. But even before it reaches such precision, another faculty has already drawn it near: its sense of smell. The tiger shark's olfactory bulbs are proportionally among the largest in any vertebrate, directly connected to the brain through thick nerve cords that process not just the presence of blood, but its concentration, age, and direction of drift. In the vast openness of the ocean, this becomes a kind of sixth sense, a navigation system guided by the scent of decay. The shark drifts along scent trails the way migratory birds follow magnetic lines. Each current carries a different signature: the oily sweetness of mackerel, the sharp iron of wounded turtle, the earthy residue of seabird droppings dissolving in tide. These cues mix and diverge like sentences carried by wind. The tiger shark, following them, can reconstruct entire events: a kill site miles away, a bleeding whale calf, a night of nesting turtles. Its journey is not random. It is an investigation written in chemistry. One of its favorite haunts lies near the sandy shallows of tropical coasts, where sea turtles crawl ashore to nest under moonlight. The shark does not need to see them. It knows the rhythm of the season, the subtle increase of organic scent near the shore, the muffled thumps of flippers against wet sand. Turtle nesting season is a buffet masked as a miracle. The sharks patrol the periphery, rarely breaching shallow depth, but constantly listening to the low-frequency disturbances that signal activity. Each nesting event creates what marine biologists call an alarm zone, a region of elevated risk where predator and prey overlap by timing rather than geography. The shark's presence here is not coincidence. They are patient custodians of inevitability. When a turtle finishes laying eggs and returns to the surf, it drags a wake of fatigue and scent. Muscles exhausted, movements sluggish, it becomes a target. The tiger shark can detect the iron traces from torn skin where the turtle scraped coral on its ascent, or the burst of carbon dioxide that signals exertion. Using its lateral line system, a series of pressure-sensitive canals running the length of the body, the shark can even detect the minute vibrations of the turtle's flipper strokes, distinguishing them from the random turbulence of waves. In darkness, where visibility drops to zero, this sensory suite creates an almost three-dimensional awareness of movement and direction. It does not need eyes to hunt. It reads the water as if it were braille. But this predator's genius lies not only in direct pursuit. The tiger shark is an opportunist, an oceanic scavenger that uses intelligence rather than endurance to maximize its advantage. When other hunters, like dolphins or smaller sharks, make a kill, they release a plume of scent and tissue into the water that can travel kilometers. Within minutes, the tiger shark intercepts this invisible trail. Guided by alternating currents and the Earth's own magnetic gradients, it navigates directly toward the source, often arriving just as the original predators finish feeding. Instead of fighting for scraps, it reads the remaining cues, eddies of disturbed sand, fragments of flesh still descending, to reconstruct where and how the kill occurred. This behavior, known among researchers as kleptopredation, gives the tiger shark its reputation as the bait reader, a predator that hijacks the aftermath of another's work with surgical timing. The strategy saves energy, which is vital for an animal that can weigh nearly a ton and patrol thousands of kilometers of open ocean. Energy conservation in large marine predators is not laziness, it is efficiency honed by evolution. The ocean offers abundance and emptiness in equal measure, and only those who know when to act and when to wait endure. The tiger shark's metabolism is slow, its liver enormous, accounting for nearly a quarter of its body weight, and serving as both buoyancy aid and energy reserve. This liver stores oils rich in squalene, allowing the shark to maintain neutral buoyancy and glide for hours with minimal effort. When combined with its opportunistic feeding, the result is a creature perfectly adapted for long, calculated existence rather than reckless pursuit. It is not only the chemistry of scent that guides the tiger shark, but also the acoustics of environment. In shallow bays and tidal zones, sound behaves unpredictably. The crash of waves, the hiss of shifting sand, the echo of reef fish all combine into an underwater symphony of noise. The shark exploits this chaos. When hunting near coasts, it times its movements with the rhythm of tides and surf. The rumble of waves breaking masks the vibrations of its approach, concealing it from prey that might otherwise sense disturbance through their own lateral lines. This behavior, often observed near turtle-nesting beaches, turns the very noise of the ocean into camouflage, an auditory cloak that allows the shark to strike unseen and unheard. To a turtle or a ray resting in the shallows, the danger seems diffuse.
The surf itself is loud and turbulent. Every wave feels like a heartbeat, every pulse of current a phantom.
The tiger shark glides through this sensory confusion, its striped body flickering in the filtered light, patterns breaking the silhouette that would betray its shape. When it finally lunges, the attack is explosive, not from distance, but from stillness, a burst of acceleration powered by the contraction of deep red muscle and the whip of the tail. Its jaws, lined with serrated teeth shaped like can openers, close not in a single bite, but in a sawing motion that can shear through bone, shell, and even metal debris. In seconds, the water returns to stillness, the noise of the tide covering the violence beneath. The tiger shark's adaptability extends beyond tactics to diet. It is one of the most eclectic feeders in the marine world, consuming everything from seabirds and crustaceans to carrion and garbage. This indiscriminate appetite has earned it the nickname the ocean's dustbin, yet such versatility is a product of evolutionary genius. In ecosystems defined by scarcity and unpredictability, dietary flexibility ensures survival. Where reef sharks rely on fish and hammerheads on rays, the tiger shark endures when others starve. Its stomach, elastic and highly acidic, can digest even hard keratin and cellulose from sea turtles or albatross remains. Studies of stomach contents have revealed objects as strange as license plates and tires, evidence not of confusion, but of opportunism. For the tiger shark, anything that smells like biology is a potential meal. Despite this, the shark's role in the ecosystem is far from destructive. It is an essential regulator of marine health, removing weak, sick, and dead organisms from circulation. Its scavenging prevents the buildup of decaying matter that would otherwise foster disease. By preying on the vulnerable rather than the strong, it indirectly strengthens prey populations, ensuring that only the fittest reproduce. In coral reef systems, tiger sharks even influence the behavior of other predators, creating what ecologists call a landscape of fear. Their presence alters where smaller sharks and fish feed, reducing overgrazing in certain areas and allowing seagrass meadows to recover. Through fear alone, they sculpt the behavior of entire communities. Yet there is an intelligence to this fear, both in those who feel it and the one who inspires it. In recent years, tracking studies have revealed that tiger sharks follow highly specific migration routes aligned with seasonal prey abundance and ocean currents. Some travel thousands of kilometers between feeding and breeding grounds, using the Earth's magnetic field as a compass, a biological magnetoreception that functions even when visual or olfactory cues fade. Their movements are timed to environmental events, whale calving seasons, turtle migrations, mass fish spawns. To call it instinct simplifies what is truly pattern recognition on an ecological scale. They do not chase life blindly, they predict it. Under the surface calm, the tiger shark's world remains one of mathematics and momentum. Every pulse of current, every trace of scent is a variable in a larger equation. Where other predators dominate through force or speed, the tiger shark dominates through reading, of chemistry, of physics, of the subtle conversations between death and opportunity. It is not the ocean's brute, but its analyst, its interpreter. As dawn breaks over the nesting beach, the last of the turtles returns to sea. The surf thickens with foam, and beyond the breakers, a single dorsal fin cuts briefly through the light before disappearing again. The predator moves on, leaving only the faint trace of disturbed sand and a few drifting scales in its wake. The tide rolls back, erasing even that. The ocean, once again, appears still, its surface concealing the reader below, gliding quietly through the endless text of water, scent, and sound. At dawn in the shallow lagoons of northern Australia, the sea appears empty, a pane of glass stretched between the mangroves and the coral fringe. The water is so clear that even the shadow of a leaf seems to float suspended in midair. But below the surface drifts a predator that almost no one can see. It has no bones, no brain in any conventional sense, and no sound to announce its presence. Yet every movement it makes is precise, deliberate, and, for the creatures it hunts, final. The box jellyfish, a near-perfect embodiment of invisibility and lethality, patrols these tropical shallows like an assassin made of light. Its body, or medusa, is shaped not as a bell, but as a cube, 4 smooth, translucent walls meeting in rounded corners, each side edged with tentacles that hang like curtains of glass thread. Even in bright sunlight, the jellyfish is nearly impossible to detect. Its tissues match the refractive index of seawater so closely that it vanishes against its surroundings. Only when the sun hits at just the right angle do faint glints betray the presence of something moving, something alive. The predator's camouflage is not an adaptation of color, but of physics, an evolutionary invisibility cloak based on how light bends through flesh and water. This transparency is more than defense. It defines how the box jellyfish hunts. Unlike most of its drifting relatives, it is not a passive organism waiting for prey to blunder into its tentacles. It is an active directional hunter capable of pursuit and avoidance. Within the margins of its cube, it holds an astonishing secret: 24 eyes arranged in clusters called ropalia. Each ropalium contains 6 distinct eyes, including 2 with lenses capable of forming true images. These image-forming eyes are oriented horizontally, giving the jellyfish a panoramic awareness of its surroundings. They are not connected to a centralized brain, but to a distributed nerve ring that processes visual data locally, allowing the jellyfish to respond instantly to obstacles or targets without higher thought. Through these eyes, the box jellyfish can distinguish between open water, reef, and mangrove roots. It swims with purpose, pulsating its bell to navigate towards sunlit regions where juvenile fish gather. This behavior alone sets it apart from nearly every other jellyfish species, which typically drift wherever the current carries them. The box jellyfish moves like a stealth drone, using visual feedback to weave between coral outcrops and avoid stranding in the shallows. Researchers observing this behavior describe it as a form of primitive vision-guided navigation, though the effect is eerily sophisticated. Without a brain, without even neurons in the conventional sense, the jellyfish demonstrates choice. Its tentacles, long and translucent, are strung with thousands of specialized stinging cells called nematocysts. Each one is a microscopic weapon, a coiled harpoon tipped with toxin, held under immense pressure. When triggered by contact or chemical cues, the cell fires in less than a millionth of a second, launching its barb with a force that rivals a bullet's acceleration. The venom floods into the victim's tissue through hollow tubules, delivering a cocktail of proteins that attack the heart, nervous system, and skin simultaneously. In small prey, such as anchovies or shrimp, paralysis is immediate. In humans, a single encounter can be fatal within minutes, but the box jellyfish's tentacles are not haphazard nets. They are precise tools controlled independently by the animal's peripheral nerve network. When it detects motion nearby, perhaps the minute flick of a fish's fin, it spreads its tentacles outward into a broad curtain, a wall of invisible death suspended across the current. The jellyfish can then contract or retract specific sections, tightening its trap around the moving target. Once contact is made, the tentacles constrict, wrapping the prey in a tightening embrace as nematocysts fire in sequence. Within seconds, the captured organism goes limp, its body already digesting externally as enzymes begin breaking down tissue before ingestion. The box jellyfish then pulls its meal toward its central arms, where the liquefied prey is absorbed. It is silent, efficient, and merciless, a hunter without expression, driven only by perfect sensory logic. Evolution has honed this efficiency for hundreds of millions of years. The earliest jellyfish ancestors predate dinosaurs, surviving every mass extinction since the Cambrian. Over time, box jellyfish diverged from their passive kin, evolving stronger muscles for propulsion, a decentralized nervous system capable of visual processing, and one of the most potent venoms known in the animal kingdom. That venom is a molecular masterpiece of speed and precision. It contains porins, proteins that punch holes in red blood cells, and ion channel modulators that disrupt nerve signaling. The combination floods the bloodstream with potassium, causing a rapid drop in blood pressure and cardiac arrest. Victims often die not from pain, but from a heart that simply stops obeying commands. The lethality of this venom is not intended for creatures as large as humans. Its design is proportional, to immobilize small, fast-moving prey before they can escape and tear the fragile tentacles. Efficiency, not cruelty, drives the chemistry. But for humans who enter these waters unaware, swimmers, divers, or children wading near shore, the effect is catastrophic. Contact with even a few meters of tentacle can send pain surging through the body in waves of burning heat. The scars left behind form whip-like patterns that map the route of each tentacle across the skin. Among the most feared members of this lineage are the smaller, nearly invisible species of the genus Carukia, responsible for what is known as Irukandji syndrome. Named after an aboriginal group whose coastal lands intersect with the jellyfish's range, this condition represents one of the strangest forms of envenomation in nature. The sting itself is often mild at first, a slight prick, perhaps mistaken for a sea lice bite. But after a delay of up to half an hour, the real agony begins. The venom triggers a massive release of catecholamines, stress hormones like adrenaline and noradrenaline, sending the body into physiological overdrive. Heart rate soars, blood pressure spikes, muscles cramp violently, and victims experience a suffocating sensation of impending doom. Many describe it as the feeling of dying without actually dying. The irony is that the jellyfish itself is scarcely larger than a fingernail. The Irukandji's delayed attack is an evolutionary inversion of most predator strategies. In nature, speed is typically the goal. Strike, paralyze, consume. But the Irukandji's venom operates as a cascade, overwhelming the victim's system in waves rather than all at once. The purpose of this delayed onset may lie in its ecological role, a mechanism to subdue larger, more energetic prey like fish larvae or small crustaceans that would otherwise escape if paralyzed too soon. The venom's slow burn ensures that by the time full immobilization occurs, the prey has already exhausted itself within the tentacle's reach. What feels to humans like malicious irony is, in truth, evolutionary optimization. Despite their danger, box jellyfish are integral components of their ecosystems. They regulate populations of small fish and plankton, influencing nutrient distribution across coastal systems. Their presence also shapes the behavior of other species, even turtles, some of their few natural predators. Sea turtles possess thick skin, resistant to the jellyfish's venom, and often consume them in large numbers. Their feeding in turn helps limit jellyfish blooms, maintaining balance in the food web. This relationship underscores a recurring theme in marine ecology, that even the most feared organisms occupy a stabilizing role within the grand design of the ocean. Yet the balance is fragile. Climate change, warming waters, and human interference have extended the range of box jellyfish farther south along Australian coasts. Increased development near mangrove zones where juveniles mature has brought people directly into their habitats. The same transparency that makes them perfect hunters makes them perfect accidents waiting to happen. In response, scientists have developed new tools to track their movements: sonar mapping of jellyfish swarms, infrared imaging, and molecular tests for venom residues in the water. Still, the ocean's translucence protects its assassins well. To see one in the wild, truly see it, is to confront how alien life can be even on Earth. The jellyfish pulses with hypnotic rhythm, a faint blue shimmer marking each contraction. Its cube-shaped body drifts in the tide like a ghost lantern, delicate yet precise. Around it, a faint halo of refracted light bends as if the water itself were distorting. There is no sound, no ripple. Only when the tentacles brush a passing fish does the silence break. A twitch, a flicker, then stillness. The curtain closes, and the predator resumes its slow, transparent patrol. For all its simplicity, the box jellyfish reveals how far evolution can stretch the definition of intelligence. It is a body of nerves without a brain, a hunter without thought, yet capable of sight, decision, and perfect timing. It navigates by light it cannot interpret consciously, kills with chemistry it does not understand, and thrives in waters where visibility is both a gift and a weapon. It is a contradiction made flesh, or rather made gelatin, an organism that turns absence into advantage. As the morning brightens, the lagoon begins to sparkle with reflected sunlight. The box jellyfish disappears completely, its cube dissolving into the glare. Fish continue to dart, unaware that death moves between them. For those who live by sight, the jellyfish is a myth. For those who understand the sea, it is the reminder that the ocean's deadliest hunters are often the ones you never see at all. In the turquoise shallows of the Indo-Pacific, the sea seems calm, almost domesticated. Beneath the surface, soft rays of light dapple the coral gardens, fish shimmer like living confetti, and the rhythmic sway of seagrass moves in time with the tide. Yet within this serene landscape glides a creature that blurs the boundary between land and ocean, between serpent and fish, a predator shaped by evolutionary paradox. The sea snake, elegant and otherworldly, coils and uncoils through the water like a silk ribbon caught in slow current. It is a reptile that has abandoned land almost entirely, trading scales for hydrodynamics, lungs for patience, and venom for precision. But for all its mastery, it remains haunted by confusion, both in its own eyes and in the eyes of others. The story of the sea snake begins with identity, and how evolution has both refined and complicated it. Belonging to a group of more than 60 species spread across the warm tropical waters of the Indian and Pacific Oceans, sea snakes are among the most specialized of all reptiles. Their lineage traces back to terrestrial ancestors that once slithered across beaches and mangrove roots, venturing into tide pools for food. Over millions of years, those hesitant forays became permanents. Limbs disappeared, scales flattened, and the body reshaped itself into a torpedo of muscle and grace. The result is a creature that swims as effortlessly as any fish, yet still breathes air like its terrestrial kin. It is this dual nature, reptile physiology bound to a marine life, that defines both the sea snake's genius and its vulnerabilities. When it rises to the surface, It must break the water's skin with its snout to take in oxygen. But unlike most air-breathing creatures of the sea, it does not need to surface often. The sea snake's lungs extend almost the full length of its body, acting as both oxygen reservoir and buoyancy control. Even more remarkably, its skin has evolved to absorb dissolved oxygen directly from seawater, a feature found in few other reptiles. Nearly 1/5 of its oxygen intake comes through the skin, allowing the animal to remain submerged for hours, motionless, invisible, waiting where its prey cannot see. Patience is the sea snake's currency. It hunts in silence, drifting among corals or weaving through schools of small fish, striking only when success is guaranteed. Its fangs, short but needle-sharp, deliver venom among the most potent in the natural world, a neurotoxic blend that can paralyze prey in seconds. Yet it rarely wastes a bite. Efficiency governs every action, for oxygen is finite, and unnecessary struggle burns what it needs most to live. This delicate balance of control defines the sea snake's every encounter, especially during the chaotic season of reproduction, when precision collapses into confusion. As the monsoon winds shift and coastal waters warm, male sea snakes enter their breeding frenzy. Hormones flood their systems, and instinct replaces restraint. Driven by the same imperative that governs all life, males patrol shallow reefs, scanning for the sinuous silhouette of a potential mate. But their vision, though suited for the dim blues and greens of underwater light, is easily deceived. To a male sea snake, almost anything long and undulating can resemble a rival or a receptive female. Even the fins of divers, the tails of eels, or the wavering reflections of their own species in a mask lens. These misreads have made sea snakes infamous among swimmers and scientists alike. Reports of snakes attacking divers are often misinterpretations of their own mistakes. The truth is far stranger and far more innocent. During breeding season, males frequently mistake human legs or flippers for competitors or mates, approaching them with uncharacteristic boldness. They circle, brush, and sometimes attempt to entwine, a behavior that, though unnerving, is not aggression but misplaced courtship. Observations reveal that males even follow non-living objects if they mimic the right size and motion pattern. For the snake, shape and rhythm are more reliable cues than species. Evolution has made them exceptional hunters but imperfect lovers. Underwater, these misidentifications can lead to what biologists call competitive escalation. When multiple males converge on a perceived female, real or otherwise, they spiral together in twisting combat, their bodies knotting and looping as they try to assert dominance. These writhing masses of muscle can last for minutes, sometimes hours, until one emerges victorious or the illusion dissolves. Energy is burned, oxygen depleted, and the risk of predation rises. Yet this is the cost of reproduction in a world where clarity is scarce. Even in these moments of confusion, the sea snake's design ensures it can survive the aftermath. Its oxygen management, perfected over millions of years, allows it to linger near the seabed to recover, its heartbeat slowing, metabolism dropping to a crawl as it drifts back into stealth. That same mastery of stillness shapes how it hunts. Sea snakes often rely on ambush, positioning themselves at the mouths of reef crevices where small fish hide. Their coloration, a pattern of pale bands or honeyed stripes, breaks their outline against the corals. Many species also use their tails, broad paddle-like appendages evolved into natural oars, as decoys. When the snake rests with its head buried in rock, it flicks the tip of its tail in gentle undulations. To nearby fish, the motion mimics the struggling movements of a worm or shrimp. Drawn by the apparent opportunity, they approach, only to find themselves within striking range of the snake's hidden head. This behavior, known as caudal luring, exemplifies evolutionary deception, using the tail not as propulsion but as bait. The tail's design also tells the story of adaptation at the molecular level. Composed of flattened vertebrae and reinforced musculature, it serves as both rudder and propeller, allowing the snake to maneuver with precision unmatched by any terrestrial relative. Yet the modification carries a trade-off: reduced mobility on land. Unlike sea kraits, which still crawl ashore to lay eggs, True sea snakes have lost that option entirely. They are fully marine, giving birth to live young underwater. The transformation is complete. There is no going back to land. In the hierarchy of ocean predators, sea snakes occupy a niche between stealth and specialization. They feed primarily on small fish, eels, and crustaceans that dwell in the complex topography of coral systems. Their vision may not rival that of sharks or dolphins, but their chemical senses are acute. Tiny pits along their snouts detect dissolved molecules in the water, allowing them to follow prey trails even in darkness or turbidity. When they strike, they rely on rapid venom delivery rather than brute strength. Once the neurotoxin takes effect, the prey's muscles lock, and the snake simply waits for the paralysis to finish its work. Sea snakes have few natural enemies. Large predatory fish such as sharks and groupers may take them occasionally, but their venom and agility make them risky targets. Sea eagles and ospreys, however, have learned to exploit their need to breathe, snatching them from the surface during respiration. Even here, evolution provides a countermeasure. Sea snakes can hold air in their lungs with remarkable efficiency, exhaling and inhaling in under 2 seconds before diving again, a maneuver so fast that predators often misjudge the timing. Their interactions with humans remain a study in irony. Despite possessing venom capable of killing a person within hours, sea snakes are among the least confrontational animals in the ocean. They rarely bite unless handled or trapped, and even then many bites are dry, venom withheld deliberately. This restraint may stem from the evolutionary cost of wasting venom, which takes energy to produce and is reserved for feeding, not defense. In essence, they are predators built for precision, not chaos. Beyond their individual adaptations, sea snakes serve as ecological indicators. Their distribution and abundance reflect the health of coastal ecosystems, particularly coral reefs and seagrass beds. Declines in their populations often signal degradation from pollution, overfishing, or rising ocean temperatures. As apex mesopredators, they regulate smaller prey populations, maintaining balance within the reef community. When reefs die, so too do the snakes that depend on them, a reminder that even the most efficient designs cannot outpace environmental collapse. Watching one in motion is to witness nature's quiet engineering at its most refined. The body flows like liquid geometry, each curve a function of pressure and thrust, each flick of the tail a correction in balance. Sunlight ripples over its scales, refracting into patterns that shimmer and vanish with every movement. There is no wasted motion, no visible effort. Even its surfacing for air seems choreographed. A brief rise, a faint ripple, and then disappearance again beneath the glare. In this world of misinterpretation, where fins become rivals and tails become bait, the sea snake survives through discipline, not dominance. It is a lesson in evolutionary compromise, a reptile that conquered the sea by surrendering land, a hunter that thrives by knowing when to be still. When the waters calm after a storm, or the reefs hum with new life, it returns to its silent patrols, reading the language of currents and light that few others can decipher. And in that shifting, refracted world, the line between predator and phantom blurs once more, the mistaken identity perfected by evolution itself. The tide falls away from a broad tropical sand flat, leaving behind a mirror of shallow water that glows beneath the morning sun. Small ripples glide across the surface, stirred by the wind and the faint tremor of unseen life beneath. From above, the scene appears tranquil, unbroken. Only the faintest discoloration hints that the sand below might be more than sand. For hidden beneath a fine layer of silt lies one of the ocean's most refined ambush engineers, the stingray. Its body merges seamlessly with the seabed, edges dusted with sediment until it becomes part of the terrain itself. Only 2 small protrusions, the spiracles, tiny breathing vents behind its eyes, betray its presence, pulsing gently as it draws water over its gills. The stingray does not move, yet it is acutely aware. Every heartbeat, every flicker of fin from nearby prey sends ripples through the electric field. It senses as easily as we sense sound. The stingray's design is an exercise in evolution's minimalism, a living shadow sculpted by hydrodynamics and stealth. Its flattened body, formed from fused pectoral fins, allows it to glide effortlessly across the seabed and settle with near-perfect stillness. This shape minimizes turbulence, enabling it to remain hidden even as currents shift. Once buried, the ray's camouflage is so complete that even experienced divers can hover a meter above one and never notice. But stillness is not passivity. Beneath the sand, the stingray's sensory world vibrates with information imperceptible to others. At the heart of this perception lies one of nature's most extraordinary systems: electroreception. Along its snout and mouth are hundreds of tiny pores known as ampullae of Lorenzini, specialized organs capable of detecting minute electrical fields generated by the muscle contractions and nerve impulses of other animals. Every living creature, no matter how silent or still, gives off an electric signature. For the stingray, this field is as visible as color, as directional as scent. A buried ray can sense a flounder or shrimp moving under a layer of sand, or even detect the rhythmic pulse of a fish's gills meters away. This capability allows it to strike with precision long before its prey realizes danger is near. The electroreceptive field also functions as a kind of lie detector. Prey fish often attempt to remain perfectly still to avoid detection, freezing their movement in the hopes of vanishing into the substrate. But even immobility cannot mask the electrical whisper of life, the faint, constant current of cells in motion. The stingray reads this signal instantly, distinguishing between the living and the inert. Its attack begins not with movement, but with calculation, a three-dimensional understanding of the prey's location, depth, and orientation. The ray's body tenses like a drawn bow, muscles coiling beneath the sand. When it strikes, the transformation is explosive. The ray beats its wings in a single thunderous motion, creating a cloud of silt that erupts outward like an underwater detonation. In that instant, the once invisible shape becomes a whirling vortex of energy. The water churns into concentric rings of debris, the dust ring, a phenomenon that can momentarily blind observers, but gives the predator total control. From within this eruption, the stingray's mouth opens on the underside of its body, forming a suction vortex that pulls prey toward crushing plates of cartilage. These plates are not sharp, but broad and ridged, designed to grind the shells of mollusks, crabs, and small crustaceans. For fish caught in the blast, escape is impossible. The suction is too strong, the timing too precise. The dust ring attack is one of the stingray's most efficient predatory displays. It uses not only raw speed but hydrodynamic manipulation, weaponizing the physics of displacement and low pressure. The ray's wide pectoral fins act like giant fans, forcing water outward and then drawing it back in with vacuum-like force as the body settles again. This two-phase motion allows it to bury itself anew within seconds, ready to strike again. What appears as a single graceful movement is in fact an orchestrated cycle of energy conservation and precision strike, a behavior refined through millions of years of evolution. But while its hunting strategy embodies precision, the stingray's defense tells another story, one of last resort. Along the base of its tail lies the barb, a serrated, venomous spine sheathed in thin skin. Contrary to popular perception, this weapon is not used casually. The barb is a defensive adaptation, not an offensive one. Its placement makes it effective only at close range, typically against predators that corner or grab the ray. When threatened, the stingray arches its body and flicks its muscular tail upward in a whip-like motion. The spine drives forward in a stabbing thrust, capable of penetrating thick skin or even bone. The barb's mechanics are intricate. Each spine is made of dentin, the same material as human teeth, reinforced with layers of mineralized tissue that form microscopic serrations along its edges. These serrations point backward, ensuring that once embedded, the spine resists removal. Venom glands at the base release a protein-based toxin that causes immediate pain, swelling, and tissue damage. For natural predators such as sharks, this deterrent is often enough to end an attack. For humans who inadvertently step on or handle rays, the injury can be serious but rarely fatal. The stingray's venom is not designed to kill large animals. It is designed to teach distance. Still, its reputation as a dangerous creature has often overshadowed its ecological importance. In truth, stingrays are vital components of coastal and benthic ecosystems. Their feeding behavior stirs up sediment, redistributing nutrients and oxygenating the seabed. This process, known as bioturbation, enhances habitat diversity, creating opportunities for smaller organisms to thrive. Where rays feed, shrimp, worms and mollusks proliferate, drawing in secondary predators like snappers and barracudas. In this way, the ray's hunt sustains a food chain that extends well beyond itself. Even the circular feeding pits it leaves behind, called stingray craters, become microhabitats, sheltering juvenile fish and invertebrates until tides erase them. The stingray's sensory sophistication also influences how it navigates the world beyond feeding. Some species, such as the eagle ray and the cownose ray, migrate over long distances, guided by a combination of magnetic cues and electroreception. Their pectoral fins act not only as propulsion, but as stabilizers, maintaining equilibrium across changing currents. In deeper waters where light fades, electroreception becomes their compass, mapping the ocean floor in signals rather than sights. Scientists believe this sensitivity allows rays to locate buried prey even under several centimeters of substrate, or to orient themselves during migrations through turbid estuaries. It is as if they possess a sixth sense attuned to the electrical architecture of the planet itself. Despite their evolutionary success, stingrays live precarious lives in proximity to humans. Coastal development, fishing pressure and habitat loss threaten their populations. Many species are caught as bycatch in trawling nets, their flat bodies entangled among target fish. Others face direct exploitation for meat or cartilage. In regions where mangroves and seagrass meadows are destroyed, the rays lose both their nurseries and their hunting grounds. Their decline carries silent consequences. Without them, sediments compact, nutrient cycles falter, and entire communities of benthic life diminish. The buried trap, once a symbol of patience and adaptation, becomes a casualty of speed and expansion. In natural settings, however, the stingray remains a master of subtlety. On a calm afternoon, a diver may hover above a sandy plain, unaware of the presence below. The stingray, resting under a light dusting of sediment, waits without tension. Its gills open and close in slow rhythm, its eyes scanning for shadows of passing danger. A school of mullet drifts by, their faint bioelectric fields painting soft ripples in the ray's sensory vision. It makes no move. They are too large, too wary. A few moments later, a small crab emerges from its burrow, scraping along the sand. The ray senses the movement instantly, tracking the signal as it approaches. Then, with a soundless pulse, the sand erupts. A puff of debris swirls outward, and when it clears, the crab is gone. The surface returns to calm, unmarked except for a faint circle, the residue of another perfect kill. Every element of the stingray's behavior reflects a profound equilibrium between energy and environment. It does not chase, yet it conquers. It does not roar or flash, yet its presence shapes entire habitats. It is evolution's quiet mathematician, calculating, conserving, and executing with impeccable timing. Even its sting, so often misunderstood, is a lesson in moderation. Violence only when cornered, warning instead of war. As the tide rises again, the sun fades from gold to blue, and the sand begins to shift with renewed current. The stingray lifts from its resting place, stirring a soft spiral of sediment before gliding away. Its outline vanishes almost immediately, absorbed into the texture of the water. What remains is silence, the kind that conceals precision. In that silence, the buried trap resets itself, ready once more to wait, to read, and to strike with invisible certainty. The morning tide moves through the shallows like a breath, slow, rhythmic, and heavy with suspended light. Within the wavering green of a seagrass meadow, everything sways together, a synchronized choreography of stems, currents, and shadows. Among this living forest, something else moves in near-perfect imitation. Its shape is indistinct, its motion too natural to question, its form blending with the vertical stalks around it. Yet within this illusion hides a creature so anatomically improbable that for centuries it was mistaken for myth. A fish built like no fish, armored like an insect, and governed by a reproductive reversal that rewrote the rules of the animal kingdom. The seahorse drifts between reality and disguise, a phantom sculpted by evolution's strangest logic. To find one in the wild requires a certain kind of patience. Its body, wrapped in bony plates rather than scales, refracts sunlight unevenly, catching faint glimmers of gold and olive before vanishing again into the background. It does not swim in the conventional sense. Its tiny dorsal fin vibrates so rapidly it seems to shimmer rather than move, propelling it forward at the pace of a drifting leaf. Small pectoral fins near the head adjust its balance, allowing micro-corrections with surgical precision. The tail, prehensile and muscular, coils around seagrass stems, anchoring the animal against current. In stillness, it becomes indistinguishable from its environment, a piece of living camouflage so convincing that predators often glide past without realizing they have overlooked their meal. The seahorse's posture, vertical and rigid, is its most iconic illusion. While most fish align horizontally to the pull of gravity, the seahorse's spine is bent at a right angle to its body, giving it an upright bearing. This orientation allows it to mirror the stalks of seagrass and coral it inhabits, turning invisibility into an everyday defense. Its skin can shift hue subtly, adjusting pigment cells called chromatophores to match the ambient colors of algae or coral. Some species even grow tiny filaments, dermal extensions that mimic the texture of plant tissue. The deception is complete not through perfection, but through imperfection. Like all natural camouflage, the seahorse's disguise works because it fits the chaos of its surroundings, not because it hides in plain uniformity. Beneath this illusion lies a hunter of microscopic precision. The seahorse's head, shaped like the curved neck of its namesake, conceals one of the most sophisticated feeding mechanisms in the marine world. Its long, tubular snout functions as a hydrodynamic vacuum. Unlike predators that chase or bite, the seahorse feeds through suction, a silent ambush technique refined for stealth. When a tiny shrimp or plankton drifts too close, the seahorse snaps its head forward in less than a millisecond, expanding its snout cavity and creating a sudden drop in pressure. The prey, caught in the resulting suction vortex, is drawn in and swallowed whole. The process is nearly noiseless, leaving no disturbance in the water. The strike is among the fastest movements recorded in fish, a feat achieved not by muscle power alone, but by elastic recoil mechanisms that store and release energy like a spring. What makes this predation extraordinary is its reliance on patience. Seahorses cannot chase prey. They are too slow, their hydrodynamic profile too drag-heavy for pursuit. Instead, they depend on stillness and surprise. Their eyes, capable of moving independently, scan the surroundings like periscopes, each eye tracking a different field of vision until both lock onto a target. This dual surveillance system gives the seahorse an almost panoramic awareness of movement. It is a hunter built on the principle of economy, spending as little energy as possible to gain sustenance. In ecological terms, it thrives not through aggression, but through efficiency. The seahorse's anatomy tells a deeper story about adaptation under constraint. Its body, encased in an exoskeleton of bony rings, provides protection but eliminates flexibility. It cannot flick its tail like a fish, cannot dart or flee from predators. Instead, it has evolved armor where others rely on speed. The bony plates act like natural body armor, absorbing impact and deterring smaller predators. Yet this protection comes at a cost, the loss of escape agility. To survive, the seahorse depends entirely on its environment and its camouflage, merging into the slow pulse of the seagrass meadow where stillness is safer than flight. But perhaps the most striking adaptation of all, and the one that overturns nature's usual order, is its approach to reproduction. In the seahorse's world, it is the male who becomes pregnant. This reversal of reproductive roles stands as one of the rarest biological phenomena in the animal kingdom, and it redefines the meaning of parental investment. During courtship, a pair of seahorses performs a synchronized dance that can last several days. They entwine tails, rise together through the water column, and sway in perfect rhythm with the current. The dance is not merely ritual, it strengthens pair bonds and synchronizes hormonal cycles between partners.
When the female is ready, she transfers her eggs through an ovipositor into a brood pouch located on the male's abdomen, a specialized structure lined with capillaries, rich in oxygen and capable of providing nutrients much like a mammalian placenta. Inside this pouch, the male fertilizes the eggs and carries them until they hatch. Over several weeks, he regulates the internal environment, maintaining salt balance and oxygen flow, effectively controlling the developmental conditions of his offspring. In this way, the male becomes both protector and incubator, his body serving as a living nursery. When birth arrives, he goes through a process that resembles labor, rhythmic contractions that expel fully formed miniature seahorses into the open water. Some species release only a few dozen young, while others may deliver more than 1,000. The spectacle is both gentle and violent, a quiet creature undergoing an act of intense biological exertion to ensure the next generation's survival. This role reversal challenges more than traditional reproductive definitions. It alters how the species interacts with predators and ecosystem pressures. A pregnant male, unlike an egg-carrying female of other species, can remain mobile and camouflaged. The transfer of eggs to the male pouch reduces exposure of vulnerable embryos to open water, where predation rates are high. In evolutionary terms, male pregnancy is not a curiosity. It is an efficiency strategy that maximizes offspring survival in habitats fraught with danger. By keeping its young hidden within its own body, the seahorse ensures that reproduction never breaks its disguise. Even with these defenses, the seahorse lives a precarious life. Many fall prey to crabs, rays, and larger fish that comb the seagrass beds for food. Yet their survival depends less on numbers and more on persistence. The species thrives where the environment remains stable. Shallow reefs, mangroves, and estuaries where vegetation provides both shelter and anchor points. But these same habitats are among the most endangered ecosystems on Earth. Pollution, trawling, and coastal development have stripped vast areas of seagrass, leaving seahorses exposed. Their populations have declined sharply across many regions, and millions are captured annually for the aquarium trade or traditional medicine markets. Their fragility mirrors the fragility of the ecosystems they inhabit. When the grass meadows vanish, so do the ghosts that sway within them. Yet there is resilience in their design. The seahorse's reproductive strategy allows rapid population recovery under the right conditions, and conservation programs that protect seagrass and mangroves have seen encouraging results. In some regions, artificial seagrass habitats have become sanctuaries where seahorses reappear within months. Their return is often the first indicator of ecological balance restored, a signal that the intricate web of life beneath the tides is knitting itself back together. The seahorse's ecological role extends beyond camouflage and curiosity. By feeding on small crustaceans and plankton, it helps regulate populations that would otherwise overgraze algae and seagrass. Its presence contributes to the nutrient cycling of coastal ecosystems, maintaining the delicate equilibrium between plant and animal life. In return, the seagrass offers shelter not just to seahorses but to countless other species, juvenile fish, shrimp, mollusks, forming one of the planet's most productive yet overlooked environments. Viewed up close, the seahorse's strangeness becomes logical. Every detail, from its upright posture to its reversed pregnancy, is a solution to the challenges of a complex habitat. Its quiet existence in the swaying meadows is not weakness but mastery, the art of survival through invisibility. It has achieved what few animals can, a life perfectly attuned to its surroundings, where motion and stillness, defense and disguise, predator and parent all merge into one. As the tide begins to rise again, the seagrass bends under the returning current. The seahorse releases its tail from the stalk and drifts upward, its movement slow but deliberate, its silhouette vanishing into the filtered sun. In that moment, it is impossible to distinguish where plant ends and animal begins, an embodiment of life's most enduring strategy, to disappear so completely into one's world that even predators forget to look.